Welcome to 𝐏𝐎𝐏𝐃𝐑 Study Simplified family. In today's lecture, we are going to study graph theory chapter from discrete mathematics subject. So basically, in this lecture, you are going to get all the concepts from basic to advanced. Along with that, all the gate PYQs with tricks and techniques. And if you are enjoying these lectures, if you want all the chapters, the complete coverage, in that case, you can download 𝐏𝐎𝐏𝐃𝐑 Study Simplified app and you can visit the discrete mathematics course. Links are there in the description box. You can watch this in mobile, tablet or PC. Okay, Android and Apple, both access is given. Then you can check the content section. You will get all the folders, which means all the chapters are there. Conceptual lectures along with topic wise gate PYQ is there. As you can see, graph theory, today's class, if you click on the lectures, so all these lectures which are paid lectures from this course, you are getting free on YouTube as sample. And what all lectures are covered in this video: part 1, part 2, gate PYQ on handshaking, delta theorem, then part 3, part 4, 𝐏𝐻𝐏𝐃𝐑 theorem graphs, and then part 5, chromatic number, and part 6. After that, all the lectures you can watch on the paid course. So now enjoy the one-shot series and clear all the concepts from basic to advanced and see how easy the gate PYQs are then. Okay. Welcome to new chapter, graph theory. In this lecture, we are going to study about basics of graph theory. This is part 1. These are the 4 topics which we are going to study. Let us start the lecture with the very first question. What is a graph? Everyone know this kind of figure, we say it as a graph. But for computer, what is a graph? Computer does not understand the graph diagrams, he understands maths. So as per the maths, what is a graph? Oh, so this diagram is made from vertices and sides, which we call it as edge, right? So set of vertices and set of edges is known as graph. Understood? So now if I want to write this in terms of maths, can I say my vertices are in the curly brackets P, Q, R, S, and the edges are in the curly brackets. Again, will you use the ordered pair style format or the set format? Think carefully. Here, direction is not there. If direction is not there, then order does not matter. And if order does not matter, no need to use the curve brackets, use the curly brackets. Understood? Because curly bracket says in any direction it's okay. It's like combination style. Order does not matter, but in permutation order matters, right? So for this graph, since there is no direction, order does not matter. Therefore, I'm using the curly brackets and I'm going to say my first edge is going from P to Q or Q to P. So the way of writing it is P, Q. If someone writes in this form, the normal brackets, which I say it as open bracket P, Q in the math style, closed bracket is like this. So if somebody write in this way, open bracket P, Q or ordered pair P, Q, this indicates that you are giving a direction. It is going from P to Q. But in our graph, it is not going from P to Q. It can go from P to Q or it can go from Q to P, since it's the scalar style, no direction involved. So it can go either way. And if it can go either way, we are not going to use like this. We are going to use the curly brackets. Understood? Now the rest is simple. Then you will say QR, then you will say RS, and then you will say SP. That's it. We have 4 sides. Those are our 4 edges written in the maths style. So understood? As per maths, what is a graph? Clear? Okay. And do not worry about the notes. Everything is there in the notes folder in the detail format. Okay. So when you refer the notes, this is what you will see. Vertices like this, edges like this, and we are using the curly bracket since direction not present. If direction is present, then what to do? See the next question. Tell me now, vertices are as it is P, Q, R, S. What about the edges? Will you say that now the edge is same as the previous P, Q, then Q, R, then R, S, then S, P? Answer is no. This is wrong. Then what is the edge? The edge is Since the direction is from Q to P, the ordered pair would look like this. And then we have P to S. And then we have S to R. And then we have R to Q. Okay. So this is the answer. Some might write this thing here, this thing here. That is okay. Because in the set version, again, order doesn't matter. In the complete set format, if this player is written at the last, this player is written at the first, this set will say, okay, I have no issue. But inside this set, you cannot, inside this set, we have this player. In this, you cannot say Q is written here, R is written here. That is wrong, since Q to R is not going, R to Q is going. Therefore, RQ is the right way. Understood? So, if I write in this way also, this is correct, because the direction makes sense. S to R, then R to Q, Q to P, and then P to S. Why I am writing like this? Since direction is there, therefore order matters. To the next point. Our graph can have different shapes. ABCD can be like this, or in this way, like some chips, or in this way, like some biscuits, or in this way, like some rectangle. So, all these graphs are different. The concept says computer doesn't see the graph, computer see the maths. So for maths, we don't care whether this is like square or chips or biscuit shape. Computer doesn't care. Computer only cares about vertices and edges. Okay. So computer does not, like in the graph theory, the graph does not depend on the shape. So this thing is equal ABCD, ABCD equal. This is also equal ABCD, because same vertices, same edges. But this thing you are saying equal is wrong. This thing is not equal to the above player. Tell me why. What is the reason? Reason is it is not ABCD. Check, it is ACBD. Therefore, the vertices are same. Vertices are still ABCD, but the edges are different now. Check. Here edge we have AC, right? I won't write in the open bracket. I will write the set version since direction is not there. So like this. But in the above diagram, do you have AC set? Check. AC set means this edge. So that is not present in the above graph. And therefore, this thing is completely different. It may look like they are like similar kind of player, but they are not same. They have the same vertices, but they do not have the same edges. Therefore, this graph is not same as this. Graph does not depend on shape, but it do depend on the vertices and edges. So be cautious. Understood? So this is the very important critical point. Now coming to the third point. Sometimes they give us the edge name. Instead of saying A, B, they say that edge is E1. Instead of saying B, C, they say the edge is E2. Okay, like this. So if edges are labeled, then it is called the labeled graph. Okay, then we can say the vertices are as it is, A, B, C, D, and the edges are now E1, E2, E3, E4. No need to write in this way, curly bracket, then curly bracket A, B, then B, C. No need to write like that. Simply say E1, E2, E3, E4. Makes sense? Understood? So we can go to the next topic. But before going to the next topic, a quick summary. What we have seen in the basics of graph. In graph, we have seen humans understand the diagram, computer do not. So we need the maths version. So as per the maths, graph is set of vertices and edges. Vertices are the dots, edges are the sides. You can write in the curly bracket if direction is not there. If direction is there, then ordered pair style. And it does not depend on shape, but it do depend on the vertices and edges. So keep focus on that. Third thing was, if edges are labeled, straight away write the labeled version and we will say it as the labeled graph. Okay. Now to the second concept, types of graph. You have seen recently we got two types, which was directed, having the direction, and undirected, no direction. And in your syllabus, the whole focus is on this undirected graph. We do have some questions and topics from the directed graph, but a lot of things are there from the undirected graph. You know why? Because in undirected, again, we have multiple types. So undirected, for say in a simple term, it is no direction. But deep dive inside, we have three more types. But to understand those types, we should know some basics first. Edges got two types. For now you have seen edge like this. If this is point A, this is point B, if they are connected, we say it as edge. Makes sense. Makes sense. We say it as edge, we say it as side. But this edge again have two type. What are the two type? They are parallel edge, or you may say it as multiple edge, because in some books it is written as multiple edge. And the second thing is self loop. Okay, so parallel edge, see carefully, A, B, C, D are the normal sides, the normal edges. But if you see now CD is like this, and again CD is connected like this, so multiple edges are there. So this is nothing but multiple edges or parallel edges. We can have that, we can have even 3. Okay, why so? Because in the real life you see this kind of graph, you see this kind of scenario. If you are staying at A, your office is at B, you can go directly, you can go from this road, or you can go from this road. So we have 3 ways, so 3 edges, 3 sides. Makes sense? It's connected with the real life. It's not like some hypothetical stuffs. Okay, so this is the first kind of edge, which is parallel edge. Now we have second kind of edge, which is self loop. Self loop you have already seen in the diagram, so no need to explain. I hope you know this kind of circle is nothing but the self loop. Okay, so this is the self loop. Okay, now we have 3 types of undirected graph. Undirected got 3 types: simple graph, multiple graph, and pseudo graph. Okay, this is like child, mature, parent, kind of this version. Keep that in mind. Okay, what is a simple graph? Simple graph has no special type of edges, no parallel edges, no self loop. As simple as that. Okay, so this is the simple graph. In multiple graph, multi-graph, so multi means multiple edges are allowed, but self loop is not allowed. Okay, so in multi-graph, multiple edges, parallel edges are allowed, but self loop is not allowed. You can see here. And pseudo graph is the parent, everything is allowed, every kind of child is allowed. So here simple graph is also allowed, multiple graph is also allowed, and self loop graphs are also allowed. So everything he allows. So pseudo graph is the parent graph. You can see here ABCD, it got the self loop, that is allowed. Suppose I have like this parallel edge, or you may say it as multiple edge, this is also allowed. Okay, so parallel edge, self loop, both are allowed. Now please make a note, you can see this in kind of Venn diagram style, that simple graph is inside, then comes the multi graph, then comes the pseudo graph. So what does this indicate? This indicates that simple graph do not have the parallel or self loop edges, but the multi graph do not have the self loop, may or may not have the parallel edge, which means if I have some graph which belongs to simple graph, by default it is in the area of multiple graph as well. Therefore that given graph can also be said as the multi graph. It is not like that if there is a multiple edge then only multi graph. No, this graph can also be said as multi graph, since it's like the Venn diagram, it's like the criteria. It may or may not have the parallel edges, it may have parallel edge, it may not have the parallel edge, but compulsory it should not have the self loop. Okay, so the self loop graph won't be treated as the multi graph, but the simple graph which do not have the parallel edges, okay, so may not have the parallel edges, can come inside the multi graph scenario. Now you understood why this Venn diagram is important, to understand the layers. Then comes the parent, everything is allowed, may or may not have the parallel edges or the self loop. So it's not like compulsory it should have parallel or the self loop, it may or may not have, there is no restriction. So restrictions are only there on the simple graph and multi graph. Restriction for the simple graph, no parallel, no self loop. Multi graph, no self loop. And then pseudo graph, no restrictions, may or may not have. Okay, so every simple graph is a multi-graph, because in multi-graph and pseudo-graph, since in both the areas this will come, right? Every multi-graph is a pseudo-graph, because in the pseudo-graph region this multi-graph resides. Therefore every multigraph is a pseudograph. Make sense? Easy, no complication, very simple. So only focus on the restrictions, and the other thing is like may or may not. Restrictions are very important, other things are may or may not. Okay. To the next point, some examples on SG, MG, PG. My shortcuts are like simple graph, multigraph, pseudograph. Pause the video, try, then look at my solution. Tried? Okay. So the first example is having a self loop and this parallel edge. So surely not a simple graph, because restriction was like no parallel, no self loop. Here it is present, so not a simple graph. Multigraph, definitely not, since no self loop restrictions. Here there is a self loop, so do not come to my house. It's like you are having non-veg, do not come to my house, I am vegetarian. Okay, pseudograph is like everything is allowed. What about this? What about this? Can I say, so I can basically take everything will come under the pseudograph. Okay, so no problem. Problem is there only for the SG and MG, because they got some restrictions. There is no restriction for PG, restrictions are there for the SG and MG. If I see here, I can see it as a simple graph, no problem. And yes, I can see it as a multigraph because there is no self loop. Here I cannot say as SG because there is a parallel edge, but I can definitely say MG, multigraph, because multiple edge or you may say parallel edge is there, but no self loop. So yes, this is the answer key. Easy, understood? If understood, then we can go to the third concept, degree of vertex. Now see carefully. For now you have studied vertex. We are going a step beyond that, degree of vertex. So in graph, you know which are the vertices, A, B, C, D, E, F. These are the vertices. In this concept, we are going to find the degree of that vertex, individual vertex. How to get it? Degree of vertex in short is denoted as deg of V, which is equal to number of edges incident on that vertex. Suppose this is the vertex A. If this edge is coming to him, this edge is coming to him, this edge is coming to him, one edge is not coming to him, then tell me how many number of edges are coming to him? 3. So number of edges incident on V is the degree of the vertex. So degree of this vertex A is 3. Easy, understood? If understood, now let us see by some example. But please make a note. We are going to study this concept on the undirected graph, because that is the whole kind of major topic in your syllabus. So you can see the graph as undirected graph. Now tell me the degree of this vertex A. You will say, sir, only one edge is coming to him. I know some will say, sir, our direction is not there. But our concept is designed in such a way that I have to make direction to make it simple in the explanation format. That A edge is here, who is coming? This edge is coming to him. So I have to give a direction, no, to find the answer. So I am going to say this edge is coming to A, only one edge is coming, so 1 is the answer. Degree of A is 1. What about degree of B? Degree of B, sir, again number of edges coming to him is only 1. This is the 1. Okay, so answer is 1. What about degree of C? Degree of vertex C, I can see that 1 and 2. 2 edges are coming to him, degree is 2. Degree of D, 2 edges are coming to him, degree is 2. What about F? Only 1 edge is coming to him. What about E? You will say 1 from here and 1 from this loop, right? So 2 is coming, and that is incorrect. All these things are correct because they were based on the normal edges, but for the self loop, you have to be cautious. For the self loop, we have the concept number of edges are 2. You can think in this way that you can come to this point A in 2 ways, from up and from down. So if you can come from up or down, you have 2 incident edges. You can think in that way. So number of edges in loop is 2. Easy to remember. You can come from up or you can come from down in the loop. In the edges, it is very simple. For the edges, like normal edges, it is 1. But for the self loop, the number of edges is 2. Reason is this thing. Now, if you see the question again, you might get the answer that for the edge E, the degree is 1 edge from here, see, one edge from here, one edge from up, one edge from down. So total we have 3 edges. So the degree of E is 3. Easy, understood. So for self loop, number of edges is 2. For normal edges, we have 1. Okay. Now comes the next interesting point in this. For lone vertices, or you may say isolated vertex, who do not talk to anyone, nobody comes to him. For them, the degree is always 0. Since no one is coming to him, there is no edge. See, I have this A vertex, and then there is a scenario. We have B, C, D, E, and suppose this is what it is going on, like this, F. So everyone is talking to each other in some or the other way. Everyone is having some edge, at least one edge. But this guy has no one to talk. No edge is coming. If no edge is coming, that is known as the lone vertex. That is known as the isolated vertex. And degree is always 0 there. Understood? Makes sense? So degree of this lone vertices are always, very important word, always 0. Similarly, for the pendant vertex, degree is always 1. What is a pendant? I hope everyone know what is a pendant. Generally, girl wear the pendant, boy sometimes. In the America they wear, in India I rarely see. Okay. Nevertheless, the pendant is like this. Okay. You have seen the physics pendulum oscillation like this. Yes. So pendulum, pendant, makes sense. So you have only one edge coming to this pendant. Therefore, always the degree is 1, because number of edge coming to that vertex, that pendant vertex, is 1. Therefore, the degree is always 1. Okay. Always remember that. Degree means what? Degree is how many number of edges are coming to that vertex. So here we had pendant, and only one edge was coming to that pendant always, like in this scenario, XYZ, okay, or XYZS, this is the thing, and then we have A. So A is like the pendant vertex, only one edge is coming, so degree of that is 1. Make sense? Easy. Okay, coming to the fourth concept, order and size of a graph. Okay, the basic building block is the vertex and edge. From that we are developing concepts. First concept you have seen. What was that? You have seen the degree of vertex. Okay. Before that, we had types of graph, just to make sure whatever graph we are dealing with is kind of the undirected graph, and we have 3 subtypes. That's okay, easy. But the first thing we have seen from the basic building block is degree of vertex. Okay. Now we are seeing what? We are seeing order and size of a graph. So how to find these terms? Very simple. Order of the graph is simply total number of vertices in the graph. Like in the differential equation, use that analogy. In differential equation, somebody asks you order of the differential equation. You used to say the maximum derivative term coming in the equation is the order. So here also the maximum vertices is the order. So order of the graph is what? Either say maximum or you say the total number. So total number is the maximum number, right? So total number of vertices in the graph. Count 1, 2, 3, 4, 5, 6. 6 is the answer. Easy. Sir, what about the size of the graph? So size of the graph is total number of edges. Size of the graph is what? Total number of edges in the graph G. That is your size of the graph. Now tell me. I know a lot of students will get confused. Sir, edges, I know that if I have a normal edge 1 time, self loop 2 time, and you are saying total number of edges in G. So should I find degree of C, degree of B, degree of D, degree of E, degree of F, degree of A, and then add them and say total number of edges in G? No. Total number of edges in the graph, not for a vertex. For a vertex like C, we know it has 2 edges, coming from up, coming from the side. Okay, but that is not the concept here. The concept for the size of graph is total number of edges in the graph, not on the vertex, in the graph. So in this graph, we can see a self loop. So it will get 2 edges. This is one of the edge, one of the side. This is 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 one. This is one. Right. So now count 1 plus 1. Let me write in this way. How many ones are there? 1, 2, 3, 4, 5, 6, 6 plus 1 self loop. In total, can I say 8 edges are present? Yes. So total number of edges in the graph, not on the vertex, in the graph is the size of the graph, that is 8. Understood the concept of order and size of the graph. So order, total number of vertices in the graph, size, order, total number of edges in the graph. Okay. Now there are some note for you. Point number 1. In any graph G, in any graph G, small delta, because both of the symbol are actually delta. This is, you can say, small delta, this is big delta. Okay, so small delta of G represents minimum degree of a vertex. You will have lot of vertex, right? And you will have respective degree of that vertex. Choose the minimum, and that minimum will be our delta of G, which is small delta of G. Again, we have lot of vertex. Find degree of all the vertex. Choose the maximum. So the maximum degree of the vertex will be our capital delta of G. Like for this example, tell me the small delta and capital delta of the graph. Sir, this is our lone vertex. It will have the degree 0 because no one is coming to him. There is no edge here. So that is our small delta of G. Minimum is 0. Maximum, we have 2 edges coming, here we have 2 edges coming, here we have 2 edges coming, here we have 1 edge coming, here we have 1, 2, 3 edge coming. So yes, maximum degree is for that vertex D, therefore the capital delta of G is 3. Easy, understood, makes sense. If yes, then we have second point. Since you know how to find the degree of the vertex in a graph, so in any graph G, if you find all the degree of the vertex, then the sequence you will generate is known as the degree sequence. But there is a catch. You cannot write in any form you want. Okay, degree, this. No. So degree of this sequence should be in the format of monotonically increasing or decreasing. Okay, monotonically increasing or decreasing style. So tell me, for this graph, the degree sequence in the monotonically increasing format is what? Sir, degree of this vertex is 1, 2. Number of edges coming to him 2. Number of edges coming to him, we can say 3. Number of edges coming to him is 2. Number of edges coming to him is 1, 2, 3, and this is 2. So total is 5. Total is 5. So we can say the degree sequence will be in this format, the open bracket. First write the minimum, so 2, 2. Even if it is repeated, 2 and 2 coming 2 times, write them. And then we have 3 and then we have 5. So this is the degree sequence. What is the degree sequence? First step, find all the degree of the vertices for all vertices. And then arrange in the form of ascending format, and you will say it's monotonically increasing form, and therefore this is the degree sequence 2, 2, 3, 5. Easy. So final slide of the day for the part 1, which is what all concepts we have seen. We started with a graph. What is a graph? A diagram. But for a computer, it is set of vertices and edges, right? Then we level up. We then understood that there are 2 types of number of edges, right? One type is the normal edge, where we say we have only one edge, 2 point normal side, normal line joining them, we say one edge. But if self loop is there, we say number of edges is 2. Okay. Once we understood how to find the number of edges, then we focused on degree of the vertex. Okay, so from this concept only, by using the concept of number of edges, what all we can find? We can find the degree of the vertex. Suppose I am a vertex. What's my degree? Number of edges coming to me. Okay, that is the degree of this vertex. Okay, so number of edges is a very powerful tool. With the help of that, you can find the degree of the vertex. And once you have understood degree of the vertex, then you can find the degree sequence. You can comment on the minimum degree. You can comment on the maximum degree, all those things. Apart from that, this number of edges also helps us to find the size of the graph. because size of the graph is total number of edges in the graph, not on the vertex, in the graph. This is how number of edges helped us. Vertices, it helped us somewhere, yes. Total number of vertices is the order of the graph. So order of the graph is total number of vertices. This was the summary so that you do not get confused. Vertex helped us where to find the order of the graph. Edges helped us where to find number of edges, because sometimes we have self loop, sometimes we have parallel edges, sometimes we have simple one edge, multiple like this 3 edges, right? Both the vertex got 3 edges, or in the graph itself you can say in the graph 1 2 3 edges there. Suppose a self loop, 2 edges. So number of edges finding we have understood, and from that degree of a vertex is number of edges coming to him. Size of the graph is total number of edges in the graph. That's it. So this is the summary. This is what we have seen in the today's lecture, and I hope now you are very comfortable with the terms. Somebody asks you what is degree of vertex, you know very well, for that vertex who is talking to him. Somebody asks you about the order, you know very well. Order, oh, order means correlated with the differential equation order. So maximum number of vertex, the total vertex in the graph. Okay, so in this way you can correlate and you will not get lost with the terms. So my whole and sole motto for the part 1 was to make sure you are comfortable with the terms, then we can level up in the part 2. Thank you for watching the lecture. Welcome to lecture 2. In today's class we are going to study about theorems. Basically we have 2 theorems. First theorem is handshaking theorem, second theorem is delta theorem. And I know a lot of students will say, sir, handshaking theorem, this we have already studied in the combination chapter, NC2, that was different. And in today's class, we are dealing with graph theory. So in this graph theory, handshaking theorem is different. So what is handshaking theorem, sir? Let us understand this by an example. Suppose I have a vertex. Can you find the degree of the vertex? These are my 2 vertex A and B. How to get degree of vertex? In part 1, we have studied. Suppose I am a vertex. What is the degree of this vertex? Number of edges incoming to this. Okay. So if I see this vertex, no edge is coming to him. So degree is 0. Similarly for this vertex, no edge is coming to him. So degree of this vertex B is 0. What if I introduce one edge? See carefully. If I introduce one edge, then degree will come. And my concern is by how much the total graph increased their degree. If I see this vertex, now the degree is not a 0 because one edge is incoming to him. So degree has changed or increased by 1. So this is 1. So degree of A is 1. Similarly, tell me the degree of the vertex B. One edge is incoming to him. Its degree also got increased by 1. You can see here, sir. So can I say in my total graph, the degree got increased by 1 plus 1, 2. The degree got increased by 2. So if one edge insertion can increase the degree by 2, then 2 edge will increase degree by how much? Multiply 2 on both these sides. So 2 into 2 plus 4. Is this relation valid? Is this thing happening? Let us verify. Suppose I insert one more edge. Now tell me the respective degree and then total degree in the graph. Sir, if I check now the degree of vertex A, 2 edges incoming to him, so degree is 2. Here also for this vertex B, 2 edges incoming to him, so degree is 2. Total degree in the graph is 2 plus 2, 4. So can I say in this way, n edge will increase my degree by 2 into n. Check it out. This 2 was basically 2 into 1. This 4 was basically 2 into 2. What is this bracket? Number of edges. Okay. So can I say if I have n edges, then the total degree in the graph is 2n. Based on this simple logic, we have generated the handshaking theorem. But I know a lot of students will say, sir, you have taken this normal edges. What about the self loop? Self loop is also same. Suppose I have this vertex A. Degree of this is 0. If I take a self loop, now the degree is what? Degree is 2. Every self loop is equal to 2 number of edges. So you can see 2 edges is coming to this vertex A, therefore the degree of this vertex A is 2. Again, this logic is fitting, that one self loop will generate plus 2 degree, as you can see in this example. Okay, so self loop is also satisfying, normal edges are also satisfying, therefore we can do the generalization. What is the basic idea here? That n edges gives me total 2n degree. Now see carefully how I am generalizing. Let me copy this in the next slide so that you understand very well what I am going to do. Okay, I am going to say the summation of degree of all vertex. In graph we have many vertices, so every vertex will have degree value. Add all the degrees, that is nothing but summation of degrees of all the vertices. Okay, that is equal to 2e. How come, sir? See this calculation. What was this right hand side? This is nothing but summation of degrees in the graph. So summation of degrees in the graph was actually 2 times 1, 2 times 2, 2 times n, which means it is 2 times of n is what? N is number of edges. So 2 times number of edges. E represents here number of edges in the graph. Understood this handshaking theorem? Very easy. Basic idea was every edge will increase degree by plus 2. Therefore, in the complete graph, we have many vertices. So, summation of degree of all vertices is equal to twice the number of edges in the graph. This is the theorem. Based on this theorem, we have one example. Degree sequence is 0, 1, 2, 3, 4, 6. Find the size of the graph. Pause the video and think. What is size of the graph? In the part 1 we have seen. Size of the graph is number of edges in the graph. So size of the graph is basically equivalent to number of edges in the graph, which is E, and you have to find E. Okay, how to find E? When we have degree sequence, use the handshaking theorem. Handshaking theorem says summation of degree of all the vertices is equal to 2 times the number of edges. So if I see here, there are how many vertex? 1, 2, 3, 4, 5, 6. 6 vertex are there, and every vertex degree is written like this. This is nothing but our degree sequence. So first vertex have degree 0, second have 1, third have 2, and next 3, next 4, next 6. So summation of every one is like 0 plus 1 plus 2 plus 3 plus 4 plus 6, that is equal to 2e. So what is the value of e? This is 10, then 5, then 1, so 16. So 16 by 2, which is 8. Number of edges is 8 in the graph. Therefore, the size of the graph is 8. Solved using the handshaking theorem. No need to make the diagram and then check the total number of edges based on this idea that we have 6 vertex. And in that 6 vertex, each vertex have this many degrees. If a normal student try to find the number of edges in the graph, what he will do is he will first draw the 6 vertex, and then he will think, oh, first vertex is lone vertex, second vertex is pendant vertex, third vertex should have 2 edges, next should have 3, next should have 4, next should have 6, and then he will count the number of edges and then he will comment. But we can do direct answer like this with the help of the handshaking theorem. This is a very powerful theorem. No need to do all the time waste. Understood? The power of maths is to get the answer very fast without even doing the actual work. Now there are some corollaries based on this theorem. Actually only one. We make multiple out of it. Okay, that's our style. So there is only one statement. The statement says, in any graph, obviously undirected graph, in any undirected graph, number of vertices of odd degree is even. I know whenever we study first time, when I studied this first time, I was like, number of vertices of odd degree is even. What does this mean? So simply it means that total number of vertices in the graph, we have a graph, so total number of vertices in the graph having odd degree means the degree value of that vertex should be odd. Suppose this is the vertex, he has degree 2, this is not odd degree. Suppose this is the vertex, he has degree 3, 3 is odd number, so this is odd degree vertex. Okay, so that is what the odd degree represent. Odd degree represent degree of that vertex value should be odd value. So there are many such odd degrees in the graph. Okay, what you will find is number of vertices having this odd degree is always even. Yes, it is even only. You cannot get the odd. I know some student understood this thing, some student failed to understood. So I will take one example. This is a graph. We have 4 vertex A, B, C, D. What we want to check is we want to check the total number of vertex in the graph having odd degree. Is it even? Check. For that you have to find the degree of every vertex. Tell me the degree of every vertex. Degree of this vertex A is 3 because 3 edges are incoming to him. Degree of this vertex B is 2 because only 2 edges are incoming to him. Degree of this vertex C is 3. Degree of this vertex D is 2. So tell me the odd degree vertex. This is not the odd degree. This is not the odd degree. These two are the odd degree. So degree A is equal to degree C, that is equal to 3. These are our odd degree. The theorem said in any graph, the number of vertices having the odd degree is always even. So count 1, 2. Number of vertices 2 having odd degree. Okay, so number of vertices having odd degree is 2. So yes, it is even. You can take any graph, any question, any book you open, you try. Odd degree. Okay, first you check the odd degree, and then once you get the odd degree vertex, count them. How many odd degree vertex? You will always get even value. This is what the theorem says. I know you understood the theorem now, but then you will ask me the proof. Why this is happening? I have proof as well. Do not worry. So my way to explain is very simple. First, understand the definition. If you are unable to do that, simplify it. I did the simplification. If again unable to understand, take one example. Took the example. Now you understood the number of vertex counting we have to do of odd degree, and that will be always even. Now your concern is why this is happening. What is the proof behind it? See, handshaking theorem said that summation of all the degrees of all the vertex in the graph is always 2 into E, and 2 into E is always even. Isn't it so? Because E is integer, so 2 into any integer, the answer is even. So basically this value is always even. Now when I say degree of all the vertex, which means vertex 1 plus vertex 2 plus vertex 3 plus vertex 4, so on and so forth up till vertex n. Now all these vertex won't have the same even or the odd. Okay, it cannot be like everyone is even or everyone is odd. There is mix. So you can split and write. You can say this value is basically summation of degrees of the vertex which is having the odd values, or you may say the odd degrees are combined together and the even degrees are combined together. Like in the very layman terms, if I want to say, I have a sequence like this. Okay. In this sequence, I am saying summation of this thing. So this is what our summation degree V looks like. I want to split it in the form of odd degrees in one set and even degree in another set. So can I write in this way, summation of 1, 3, 5 odd players together, summation of 2, 4, 6 even players together, and then can I say this RHS is actually equal to LHS? I'm just making a separation of odd players together, even players together. Same kind of step I am doing here. I hope now you are able to understand what I am doing. There are a lot of vertex in the graph, odd degree vertex and even degree vertex. I am just doing the separation. Summation degree vertex odd one side plus summation degree of vertex even on the other side. Okay. So complete summation of them will represent our whole summation of the degree of the graph. Okay, makes sense? If makes sense, now focus. If you have vertex which is having even degree value, then if you take one vertex, if you take two, or if you take three, if you take any, their summation will always be even. Like if I have vertex A which is having even degree value 2, then outcome is even. Suppose I have vertex B which is having even degree value 4. If I do summation of both of them, still the output is even. 4 plus 2 is 6, even. If you take another vertex C having 8 as the even degree, summation of that is again even. That's what I am saying. Summation degree of vertex having even degree value is always even. If you have understood this thing, then you should keep that in mind. This is always even. Now, rearrange this expression. You will get summation degree of odd vertex is equal to even, right hand side, minus this even. So even minus even is also even. 4 minus 2, 2, even. 10 minus 6, 4, again even. So right hand side is our even. Now see the conclusion. Summation degree of odd vertex is even. What does this indicate? This indicate the number of vertex present here is compulsory even vertex. Sir, why not odd vertex? See, if it is odd, you have VA vertex taking the value as odd degree value. Let me take it as 1. So if I have just odd player, then the result is odd. Result is not even. The right hand side should be even. Now see, if I have one more vertex B having the odd degree value, let me take 3. Now add, you will get even. So number of vertex required such that summation of degree of odd vertex is even is, here you can say 2, or in general you can say even. You can check. You can take one more vertex C having the odd degree value 5, add them out. Add them out. What is the answer? Answer is 9. Answer is odd. We needed answer even. So odd number of vertex is not working here. Even number of vertex are working here, which is making my LHS equal to RHS. Making sense? So possible only when number of vertex is even. This is the corollary. What was the corollary? Let me go back and explain. Number of vertices of odd degree is even. Remember, this odd degree means vertex having a degree value which is odd. In short, said it as odd degree. What is even degree? Vertex having a degree value is even, so even degree. Understood? So number of vertices of odd degree is even. Easy. Now, based on this, we have some more things to explain. Number of vertices of even degree, is it even or odd? Is it even or odd? You have studied that number of vertices of odd degree is even only, not odd only. Even only. You have seen here, it is even only, right? Because if you take odd like this, 3 players, if you add, you will get odd answer. We need even answer. Similarly, if you take 4 player, answer you will get is 10 plus 6, 16. See, you got the even answer. So even number of vertex will help us to get that expression. So even is the answer, odd cannot fit it. We have seen. But now tell me, what about this thing? If we have even degree, then number of vertex of even degree is even or odd. If you see by example, you will get the idea that it may be even or may be odd. There is no compulsion. There is no compulsion. Example, see, I have a graph like this. Tell me the degree of all the vertex. You will say 2. All the vertex is having degree 2. So if all the vertex is having degree 2, this means all the vertex are known as even degree here. Okay. Then tell me the number of vertex. Number of vertex in this graph, 4. So we got even answer. Number of vertex of even degree is even. Okay. But what if I have shape like this, like a house? Now tell me, every vertex here have how many degree? degree is 2. Degree is 2. If for all vertex here the degree of the vertex is 2, which is even, so even degree is going on, then the number of vertices 1, 2, 3, 4, 5. Number of vertex is 5. Answer is odd. So if you are having even degree, then the number of even degree vertex in the graph can be even, can be odd, depend on the graph. There is no compulsion. But if you have odd degree in the graph, then the number of vertex of the odd degree is always even only. Understood? Now is it crystal clear? No issue. So now let me go to the next slide, because corollaries of handshaking theorem is done. Now come some interesting points to be noted. The next point to be noted is for the simple graph, because the handshaking theorem is applicable for any undirected graph, pseudo graph, multigraph, simple graph. For any graph you can use that theorem. Summation of degree value of all the vertices is equal to 2 times number of edges in the graph. You can use for any undirected graph. But now comes our second point, which is just for the simple graph, not for the multigraph, not for the pseudo graph. In simple graph, this things is going on, but I won't read it out straight away, because then you will be like, sir, I am unable to understand anything. Okay, so let me take one example and make you understand. Suppose I have 4 vertex. So can I say every vertex here can have maximum 3 edges? Check. When I say maximum, it means you cannot go beyond. This is my first edge, this is my second edge, this is my third edge. Every vertex you can check. For this vertex also, maximum you can make 3 edges. For this vertex also, maximum you can make 3 edges. You can see for this vertex also I am getting maximum edges as 3. Okay. Minimum can be 0. Lone vertex. Can we have variations? Yes. If I have pendant vertex, okay, then who is pendant? This is the pendant vertex, because only one edge. Can we have 2? Yes. Can we have 2? This is the example. Every vertex is getting 2 edges. And then this was the maximum case. Maximum everyone is getting 3 edges. But some students are like, sir, we can make 4, 5, 6 edges as well. See like this. If you do like this, then you might say here we have 4 edges. Okay, but this is not simple graph. We are talking strictly for the simple graph here. So for the simple graph, this multi edges are not allowed. So remove that. This is the only maximum possible thing which you can do on this vertex, joining every edge possible. And if you can do this, then you can do generalization, or you can comment what just happened here. We had 4 vertex, and every vertex has maximum 3 edges. We saw every example: 3 edge example, 2 edge example, 1 edge example, 0 edge example. So every vertex for this, we are saying maximum 3 edges you can create. If that is the thing, then can I say the degree of every vertex is 3? Because if suppose I am one of the vertex in the diagram, then 3 lines are coming to me. See, if I am this thing, 1, 2, 3, 3 lines are coming to me. 3 lines coming to me means degree is 3. So every vertex here is getting maximum degree 3, because we are taking the maximum scenario. Therefore, can I now do a generalization? If 4 vertex having maximum degree of all the vertex as 3, then n vertex will have maximum degree for all vertex is n minus 1. 4 vertex is 4 minus 1. So n vertex is n minus 1. Very obvious if you take some random example again. Suppose this is my one of the vertex. I cannot join this vertex by himself, because then it would be not a simple graph. Okay, I have to join with the other points. So if I join with the other points, then first point, second point, third point, fourth point, total in the graph we have 5 points, 5 vertex, but while joining I can only join maximum 4. So n minus 1 joining I can do. If n minus joining I can do, then n minus 1 maximum edges I can generate. If that is the answer, then maximum degree is maximum edges, that is 3. That is n minus 1 in general. Understood now? If understood, this was our first point in the simple graph. What was the first point in the simple graph? That the maximum number, okay, the first point was this: degree of any vertex with n vertices is at most n minus 1. Okay, degree, maximum degree, or you can say degree at most, one and the same. So maximum degree for all vertices in the simple graph is n minus 1. This is written here. Why I used the at most or maximum? Obvious reason, because we have special cases like lone vertex and pendant vertex. There variations can happen. Therefore, the term maximum or at most is used, and it is not used every time or always. Okay. Also showed you by the example. So for the first point, you should not have any problem. Now the second point is interesting. They are saying maximum number of edges is n into n minus 1 by 2. How come? You can find this using the handshaking theorem, because handshaking theorem says summation of the degree is twice of number of edges. If you can comment here on the max, then you can comment here on the max. Do you know the maximum degree of all the vertex and then summation of that? Obviously maximum degree for all the vertex is n minus 1. So summation of that would be what? Summation of that would be first vertex is having degree n minus 1, next vertex is also n minus 1 degree, third vertex is also n minus 1 degree, so on and so forth till the last. So how many such vertex we have? N vertex. So summation of this players n times is n into n minus 1. Isn't it so simple? Indices a plus a plus a. If you have n times, what is the answer? N into a. Same concept here. If you have understood this thing, then right hand side is 2e. If you rearrange, you will get the value of e as n into n minus 1 by 2. Agreed? So e is what? N into n minus 1 by 2. But remember, this is your maximum scenario. Maximum degree for all vertex is n minus 1. So summation of that would look like this. Therefore, your E answer is of maximum, and therefore we are saying, since we consider the maximum degree, our maximum number of edges, which is E, is n into n minus 1 by 2. Understood this point now? Maximum number of edges is n into n minus 1 by 2. Why? If you have understood using the handshaking theorem, it's well and good. Otherwise, you would have done this using the combination logic. Suppose I have n points. Then if I want to join all the edges, how can I do? NC2, and NC2 is what? N into n minus 1 by 2. This is already what we have studied in the combination, and same answer you are getting. Isn't it so? Yes, because if you want to make edge, you need 2 points. So from n points, select 2 points and make edge. So NC2 will do all such combination and it will give you the answer. The answer is n into n minus 1 by 2. That is the maximum, because it considers that everyone is joined, every point is joined. Understood? If yes, then we have third point. Yes, in this we have third point. What is the third point? For k regular graph of order n, n of e is nk by 2. Again, I know you will say, sir, what is this new term? K regular graph. Okay, let me explain what is a k regular graph. If in a graph, every vertex is having same degree, every vertex, very important, then you say it as a k regular graph. In technical terms, you can say if the minimum degree of the vertex and the maximum degree of the vertex is same, let us say k, then it is a k regular graph, since every vertex have same degree. As simple as that. What does this mean? If minimum is also k and maximum is also k, then every vertex is having k degree. So if every vertex have same degree, then we say it as k regular graph, because we are assuming that the degree value is k. So k regular graph. So for every k regular graph of order n, the number of edges there is n into k by 2. Any proof, sir? Obviously, we can use the handshaking theorem to arrive at the answer. See, handshaking theorem says summation of degree of all the vertex in the graph is 2 times number of edges in the graph. So summation of degree of all the vertex in the k regular graph, every vertex is having the k degree. So k plus k plus k plus k. Up till how many times? N. Order is n. So n times k is the answer. Okay, this sequence will give me nk, that is equal to 2e. So e is equal to nk by 2. That's what I said. The number of edges in the graph is nk by 2. Understood? So no torture on this topic. This topic of handshaking theorem is done. Just a last question so that you get the confidence, and then we can move forward for the next concept. Okay, I hope you have tried this question. Now it's my turn. A lot of students will say, sir, definitely this is a simple graph. Definitely, sir, that's a trap. I know what you have done is you have checked everything. You have checked everything. First, you saw 1, 2, 3, 4, 5, 6, 7. We have 7 vertex. We have 7 vertex. Okay. So if we have 7 vertex, then summation of the degrees of the vertex should be equal to 2 into e. 2 into e, which is nothing but it should be e1. So do we have summation of all the degrees here e1? Check it out. 6 plus 4, 10. And then this is 6, and this is 6, which is 12, and then 1 plus 5 is again 6, so 28 is even. This definition is matching, so handshaking theorem is matched. Okay, handshaking theorem is matched. You are happy. Second thing you are checking is, right now we have seen for in a simple graph what happens. Okay, so in the simple graph what happens is maximum degree of the vertex should be equal to n minus 1. What is n? Number of vertex. So number of vertex is 7. So 7 minus 1 is 6. So maximum degree 6. Yes. Do we know about the minimum degree? No, there is no formula for the minimum degree. Do we need to do anything about the edges here, maximum edges? No need, because we have to just verify whether this thing exists or not, whether a simple graph with this kind of degree sequence exists or not. So maximum edges concept won't help here. Just maximum degree is helping to cross verify. Yes, maximum 6 can happen, 8 cannot happen, 7 cannot happen, other things cannot happen if you are dealing with the simple graph. So a lot of students are like, yes sir, for if I see this first and the second point, I can say definitely this thing exists, simple graph exists, and this thing is true. The answer is no, because you missed the third step, which is the analysis step. Okay, so what was that analysis step? The analysis step is, we have 7 vertex, right? 1, 2, 3, 4, 5, 6, 7. They are saying 2 vertices are such that they are having 6 degree, which means they are connected to everyone. Suppose this is first and second, they are connected to everyone. Okay. Second player is also connected to everyone. If they are connected to everyone, then in the complete graph, can you find any vertex which can have degree 1? No, sir. See, this vertex is having more than degree 1, this is having more than degree 1, and obviously they will have degree 6. See, 1, 2, 3, 4, 5, 6. Here also 1, 2, 3, 4, 5, 6, because those were our 6 degree players. This vertex is having 2 degree, this is also having 2, this is having 2, this is having 2. Minimum they are having 2 other vertices. If I see minimum, there should be degree 2. They are saying minimum degree is 1. That is not possible. Since it is not possible, therefore this degree sequence is wrong. Therefore simple graph of this degree sequence does not exist. How good this question was. I hope now you understood everything. So let me take a quick recap on the handshaking theorem. So handshaking theorem basically said, in a graph you have a lot of vertex. So if you add degrees of all the vertices, it should be equal to twice of number of edges in the graph. That's all. And then we have seen multiple things. Direct question on it. Then we have seen the corollary, which says, if you have vertices in the graph, find the odd degree vertex. Mark the odd degree vertex. Now count them. It will always be even. What about the even degree vertex? It may or may not be even, may or may not be odd. It can be anything you want to as per the situation and graph. But for the odd degree, if you start to count them, it will always be even. And we have proved it. We have proved it like this. that summation of degree of odd vertices is even. That will happen only when the number of vertex is odd. Number of vertex is even. If it is odd, we fail to satisfy this equation. Okay, understood? Then we have seen the second point, which was in simple graph. We have seen two things. In simple graph, every vertex can be joined to n-1 edges, or you may say every vertex will have how many maximum edges? n-1. Okay, if that is the case, then the degree of every vertex is what? n-1, maximum degree. Minimum can be 0 because lone vertex are allowed. So maximum degree for all the vertex in the simple graph is n-1. And if you know the degree of every vertex now, then you can comment on the maximum number of edges using the handshaking theorem, that is n into n-1 by 2, or you can simply use the combination style to arrive at this answer, NC2. This was our second point, but this was only for the simple graph, not for the multigraph or the pseudograph. Then comes the third point, again a special graph, K regular graph. It happens when the minimum degree and the maximum degree is K. That happens only when all the vertex have same degree. So if that is the case, then the number of edges in that is n into k by 2. You can any day prove it, or you can simply by heart it. It's on you. Then we have seen the question. We have checked the handshaking theorem. We have checked the special property of simple graph, but it failed to satisfy the very basic concept. Okay, so you have to analyze that critical thing and then make a decision whether it is possible or not. Now coming to the last theorem of the today's lecture, that is delta-delta theorem. What is the basic idea of the delta-delta theorem? The basic idea is to comment on the average. But average of what? Average of the degree. You know how to find the average, right? Average is sum divided by n. So if you need the average of the degree, so summation of the degree divided by the total number of vertex, because degree is found from the vertex, right? So denominator should be how many vertices are there in the graph. So average degree is now summation d divided by number of vertex in the graph, which I will take it as n, and summation degree as per the handshaking theorem, it is 2e. So we can say this 2e by n, this 2e by n, this is average degree. Average degree will always lie between the minimum and the maximum degrees. Minimum degree is what? Delta. Maximum degree is what? Delta. But remember, this is the small case delta. This is the capital case delta. Okay, uppercase delta. So small delta minimum, capital delta maximum. Nevertheless, our average delta will be in this range, minimum to maximum. This is what our delta-delta theorem says. Now you would be like, sir, how simple and obvious thing it is that average will always lie between the min and the max. So what's the point? The point is the intuition. You know what's the intuition? Check. If somebody says you the order of the graph is 10 and the minimum degree is 3, can you find the minimum number of edges? Just think. You do not know any theorem and try to predict. Order of the graph is 10. This means the number of vertex is 10. Okay. So draw 10 vertex. You draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 vertex you drawn. Now they are saying minimum degree should be 3, which means lone vertex are not allowed, pendant vertex are not allowed, okay, and 2 degree vertex are not allowed. Minimum it should be 3. Then tell me at least how many edges I should create in the graph to make sure these criteria are satisfied. Isn't it very tough to comment manually? Yes. Therefore, this delta-delta theorem comes into the play and make our life easy. What it says is, we know that minimum degree is delta, small delta, maximum degree is this thing, capital delta, and your average degree value is what? Summation d by n, or you can say 2e by n. From that you can comment on the number of edges. See, they are saying delta is 3, so this thing is 3. Minimum degree is 3. And they are saying that n instead of n, they are saying order of the graph, which is nothing but n number of vertices of the graph. They are saying 10. About the maximum degree, we do not know. Okay. So if I just take this expression now, 2e by 10 is greater than equal to 3, if 10 goes there, I can say 2e is greater than 10 into 3, which is 30. Therefore, e is greater than equal to 30 by 2, which is 15. So, minimum number of edges you should create is 15, then only this criteria will be satisfied. So, your graph should have minimum how many edges? 15. You can create more for sure, but minimum it should be 15. Understood how it helps us to identify the minimum number of edges. Similarly, it can also help us to find the maximum number of edges. Suppose order of the graph is 10, delta is 3, at most how many edges you can create? Tell me. Since we know the delta theorem, we can say here minimum degree is not given. Delta, okay, so we can say summation d by n, which is 2e by n less than equal to maximum degree. Maximum degree is delta, which is given as 3. N is given as 10 because that is order of the graph. So 2e by 10 is less than equal to 3. So e is less than equal to 10 into 3 is 30. 30 by 2, that is 15. So e should be less than equal to 15. So maximum you can generate 15 edges if you want to create the graph satisfying this criteria. Understood? Last question of the day, find the minimum and the maximum degree if this is the criteria, n is 10 and e is 18. Tried? So again, using the delta theorem, this is what the theorem says. 2e, e is 18, n is 10. So this is like 3.6. 2 into 18 is 36. 36 by 10 is 3.6. So this is what I am getting. Now I am getting things in a decimal. Okay. So how to comment on the integer? From here I can say delta, small delta, is less than equal to 3.6. So if 3.6 is here, among this, who is the minimum, like the nearest integer? That should be 3. Okay. Like delta less than equal to 3.6, I need the upper limit for delta. Upper limit for delta would be the integer 3 only. Okay, so delta upper limit. The question should be delta upper limit. That's what I meant here, because delta minimum can go up till minus infinity, you will say. So I meant the upper limit for it. Okay, so upper limit would be 3. Similarly, for the big delta, capital delta, for capital delta, I can see capital delta is greater than equal to 3.6. For here, I can say what should be the minimum? Delta minimum is 3.6. Greater than that, we have many integers, 4, 5, 6 up till infinity. So the minimum value should be 4. Understood? So delta, capital delta minimum is 4, but the small delta upper limit is 3. I hope this part is clear. This is what my question actually meant. And that's it. Our delta theorem gives us the intuition on the number of edges, the min and the max, using a very basic idea of average degree. And this was our handshaking theorem, again based on a very simple concept that one edge can generate plus 2 degrees. So n edges can generate 2n degrees. So based on that, summation of degree is what? 2 times the number of edges. And that's how the theorem was generated. That's it for today. I hope you enjoyed the class. In today's class, we are going to solve gate PYQs on handshaking theorem and delta theorem. So let us start the lecture with the very first question. First question in front of the screen. Pause the video, try, then look at my solution. Right? The question says, what is the number of vertices in an undirected connected graph with 27 edges, 6 vertices of degree 2, 3 vertices of degree 4 and remaining of degree 3? We have 4 options. Now I know when you read the question, nowhere it is written that you have to use the handshaking theorem. So always remember, whenever you see questions, there won't be direct mentioning of the theorems. It's intuitive. Looking at the data, then what we have to find, you will get the thought process. You will get the idea, oh, here we have to use the handshaking theorem. Understood? So now, let us analyze the data. What is the number of vertices? Which means n I have to find. In an undirected connected graph with 27 edges. So number of edges, E is 27. Then this is very interesting. 6 vertices of degree 2. Now I have to make the table. Number of vertices and respective degree. They are saying 6 vertices are there who is having degree 2 each. Similarly, 3 vertices are there who is having degree 4. Similarly, next we have x vertices. Remaining means x, since we do not know the total count. So we'll say that remaining should be x vertices having degree 3 each. Okay, this is given. So can you find the number of vertices in the graph? Yes, we can. How? By looking at this data, degree and edges. So handshaking theorem says summation of degree is equal to twice the number of edges. So this part is done since we know E is 27. Okay, so this is 2 into 27. Now what about this thing? Summation of degree. Some students are like 2 plus 4 plus 3. Wrong. 2 plus 4 plus 3 is not summation of degree, because this data is in the form of frequency table. This is not raw data like we have seen in the class. We used to deal with the raw data. This is not raw data. Now use the statistics concept. If you want to do the summation, it would be 6 into 2 plus 3 into 4 plus x into 3. This is summation of the degree. Understood? Reason is very simple. We have 6 vertices and every vertex is having degree 2. So if you want to sum up, you will say 6 into 2. You can also do manually 2 plus 2 plus 2 plus 2 plus 2 plus 2. You will get 12, or you simply use the maths 6 into 2. Okay, 6 into 2, you will get 12. I hope you got the idea. Also concept clarity. So 12 plus 3x, that is equal to, this is what 4 and 4, 5, 54, right? Then we can say here this is 24 plus 3x, that is equal to 54. So 3x is equal to 54 minus 24, which is 30. So x is equal to 30 by 3, which is 10. When x is 10, you got this x is 10. Now they were asking a number of vertex, so add all the vertex, you will get the answer. 10 plus 3 plus 6 is 19. So option D is correct. Easy. So detailed solution is given in the notes folder. So you do not have to worry about my way of solving like a student and the proper detailed solution. Okay, so it's there in the notes folder. You do not have to make the notes. Understood? Now to the next question. Pause the video, try, then look at my solution. Tried. Now whenever you see this kind of question, I know a lot of students are like, sir, what kind of notations they are using? Is it Harvard paper or is it GATE exam? It's GATE exam. Things are very simple. You have to just focus on the data and what we have to find. Okay, concepts you know already. I hope this part is clear. So what is this symbol? This is KSI. You can say it as sky, okay, or psi. Generally K is silent. We say it as psi, but it is KSI. Nevertheless, you can take any symbol you want. Nevertheless, here they are saying G is equal to V comma E. V is number of vertex, E is the edge set. Okay, be a graph defined like this. So psi of G is equal to summation ID into D. What is ID and D? ID is number of vertices of degree D in G. Number of vertices of degree G in D in G. Okay. If S and T are two different trees with psi of S is equal to psi of T, then which of the following option is correct? So when they are saying mod S and mod T, what does this represent? This represents number of vertices or number of edges. So in general, this is number of vertices, not number of edges. Why? Reason is when they say S and T are two different trees, so S will have vertex. So mod S is number of vertices. Similarly, T is a tree. So mod T would be number of vertices. So in general, it is number of vertices. So they need the relation between number of vertices in S and T if this is the given condition. If you now analyze the things, it's pretty simple. When somebody is saying ID is the number of vertices of degree T in G, then you remember, oh, same kind of stuff we have done somewhat here, right? Summation D was what? Number of vertices into degree. Isn't it so? Summation of degree was number of vertices into degree. Same kind of format is going on. So this is nothing but summation degree. Oh, so handshaking theorem can be used, and we can say this psi of G is nothing but handshaking theorem summation degree, which is our 2 times number of edges in the graph. But your S and T are the graph of tree style. So if it is of the tree style like this, we have seen in the earlier chapters how tree style looks like. So whenever you draw a tree, suppose I have tree of 1, 2, 3, 4, 5, 5 vertex, then the number of edges are 1, 2, 3, 4, 5 minus 1. 5 vertex, edges 5 minus 1. So n vertex edges would be n minus 1. Correct. So for a tree, you can say if you have n vertex, then the number of edges is n minus 1. So based on this, now our question of handshaking theorem is changed for the tree. Since the complete question is for the tree, summation of the degree is twice the number of edges, which is twice n minus 1. Isn't it so? Because both S and T are different trees. Now they are giving this condition. If this is the condition, then what is the relation in the number of vertices? We can solve here. Let me remove. Okay. So I think yes. Okay. So now they are saying if this is the condition, then what is the relation on number of vertices? See carefully. If this thing is true, this thing is equal to this thing. So I can say this would be twice number of vertices in S would be mod S. That is equal to, this would be twice number of vertices in T would be mod T. 2 getting cancelled, minus 1, then minus 1 getting cancelled, mod S is equal to mod T. So option C is correct. Very easy, isn't it so? So you have to analyze first what things are given, then you will get the intuitive idea. Oh, this is nothing but summation degree, so handshaking theorem, this is twice the number of edges. Then they are talking about the tree. So in tree, edges is what? If you have n vertices, then the edges is n minus 1. So you can modify this formula and you can say this thing is now just n minus 1. So now this condition is given and they were asking about number of vertices relation. So you used the substitution technique and you got the answer. Very simple, easy. To the final question, pause the video, try, then look at my solution. This is not final question of the class, but of the handshaking theorem. So I should not say pause the video and try, because you know the answer straight away. Which of the following statement is or are true for the undirected graph? P and Q are the statement. P statement says the number of odd degree vertex is even. Isn't it true? Why? Because this is corollary. We have proved this, that if you have a graph where odd degree counting, if you have odd degrees, then the counting of that is always even, right? So odd degree vertices in a graph, the counting, the number of them will always be even. Q is sum of degrees of all vertices is even. Is it true? Sum of the degree for all vertex it is even. Yes. Why? Because as per the handshaking theorem, this value is equal to twice the number of edges, and edges belongs to the integer. So 2 times integer is always even. So yes, this is also true. So both of them are true. Option C is correct. Easy, understood. To the next question. This is a good question based on the delta theorem. Pause the video, try, then look at my solution. Tried? So what is happening here is we have a graph G who is having this inequality. Edge is less than equal to 3 times vertex minus 6. The minimum degree of G is defined like this, and we know in general we define as delta, small delta, like this. Capital delta is the maximum degree. As per our notation, small delta can be used. Therefore, the minimum degree of G cannot be, not possible. Smallest degree not possible. How to do it? Now you are like, sir, delta theorem said like this, that the minimum degree is less than equal to the average degree less than equal to the maximum degree, right? This is what the thing was. Now here we have inequality. So how to deal? How to get this stuff? Because summation degree by n is nothing but summation degree is as per handshaking theorem 2e. So 2e by n. So how to get 2e by n? Because this is not something like e is a function of e, then we can get 2e by n. But here the things are in inequality. So what to do? Therefore we have to analyze, and then we have to substitute. So it's a little bit time taking, but you will get the answer. Okay, so this is the formula through which you are getting the answer, but straight away substitution won't be possible. So we have to do little bit analysis. So this thing is saying e is less than equal to 3n minus 6, right? We are in search of what? This thing is 2e by n, right? So we are in search of 2e by n. How to get that? Multiply 2 on both the sides. So 6n minus 12, divide by n on both the side. So now this is 2e by n is less than equal to 6 minus 12 by n. Okay, so we got the idea. 2e by n is less than equal to this thing. So tell me the maximum possible value of 2e by n. The maximum possible value would be n0, no, then not defined, n1, then negative, no degree, average degree cannot be negative, then 2 would be 0 is not the maximum, since because when n is 6, then we are getting some positive degree value which is greater than 0, but the maximum degree value you will get when n is 12. When n is 12, then this is gone 1, so 6 minus 1 is 5, which means this value will be maximum 5. Okay, this value maximum would be 5, right? See carefully. Why it would be 5? When n is equal to 12, then 2e by n is less than equal to 6 minus 12 by 12, which is 6 minus 1, which is 5. So 2e by n can be maximum 5. Then it can also be like 4, 3, 2, 1, 0, but it cannot go below 0, right? This is what I'm getting the idea. This is what I have analyzed. Now, they were saying minimum degree of G cannot be. If this value is 5, then phi should be greater than equal to delta, or you can say delta should be less than equal to phi. Delta should be less than equal to phi. 6 cannot happen. Minimum degree of G cannot be 6, since if we choose this as the maximum, then we got the upper limit for delta, and once we got the upper limit for the delta, then we can say phi is the ceiling. You cannot go beyond phi. Okay, so 6 cannot happen, therefore option D is correct. Makes sense? Easy. Now if you might say, sir, what if we take n is equal to 4, then 6 minus 3 will happen, so this would be 3. Agreed. For that, upper limit of delta is 3. Then you, sir, then 5 and 6 is not possible. But I am saying the maximum upper limit is what? The maximum upper limit is 5 when n is 12. So if maximum upper limit is 5, you have to focus on the max, right? You have to focus on the max only. What is the maximum upper limit for the delta? It is 5. So beyond 5 it can never go. Therefore 6 it can never go. Understood? So that is the answer. Detailed solution is given. Now to the next question. Pause the video, try, then look at my solution. Tried. G is an undirected graph with n vertices and 25 edges such that each vertex of G has degree at least 3. The maximum possible value of n is. The maximum possible value of n is. Okay, so if that is the thing, again, which theorem to use? No theorem is mentioned, but see, they are saying G has degree at least 3. Minimum degree is 3. Delta is 3. Okay, so delta is 3. E is 25. N is the number of vertex, and you have to find the possible maximum value of n. No problem. So we know as per the delta theorem, the small delta is less than equal to 2e by n, right? Now this is 3, e was given as 25, n, so rearrange, n is less than equal to 2 into 25 divided by 3. So 3 ones are, okay, here it won't be like a proper answer, so we have to use the calculator. 50 divided by 3, it would be 16.66. So 16.67. So n is less than equal to 16.67. If ceiling is 16.67, which is the closest integer? 16 is the closest integer, right? See, this is 16, this is 17, and this is 16.67. So if n is less than equal to 16.67, the maximum possible integer is 16. So that is the answer. I am giving you very step-by-step explanation so that even if diploma students are watching, they should not get issue. Therefore, I am giving you very step-by-step solution. 16 is the answer. I hope this part is pretty much clear. And that's it. Thanks for watching the lecture. Welcome to lecture 3. In today's class, we are going to see special types of graph. But before going to that, I have a question for you. The question is, this is a degree sequence. Can it be converted to simple graph? Pause the video, think. I know what you are doing. You are using the handshaking theorem. You are using the corollary that if we have odd degree, counting of them, is it even? If yes, matched. If no, wrong. then you are doing analysis also, and it's a very time taking process. And therefore you should not do all these things. You should use a simple trick, which is nothing but 𝐏𝐻𝐃𝐑𝐦 theorem, to get answer very fast. Sir, how to do it? If I just read this algorithm, you will be like, oh, it's a very boring lecture. So I will show you first and then we'll read. Okay. So we have this question. Basically, a degree sequence is given. You have to write that in the form of non-increasing format, simply decreasing format. Okay. So is it decreasing format? Obviously. So already they are giving us in the decreasing format. So now the first step is done. Write the given degree sequence in the decreasing format. Now the second step is very important. You can understand this in this way, that our first element dictates. It says take out 3 chocolates from the next element such that every element is just giving me one chocolate. Okay. So subtract 1 from the next, subtract 1 from the next, subtract 1 from the next, and stop, because only 3 chocolates you have to take outside. Okay. So now our sequence looks like this is gone. Next players are like 3 minus 1, 2, 2 minus 1 is 1, 2 minus 1 is 1, and then we have to now sort this degree sequence in the form of non-increasing style, which means a decreasing style. So 2, 2, 1, 1. Again, repeat the process. The first element says take 2 chocolates from every element such that every element is giving 1. Okay. So minus 1, stop. 2 chocolate is taken outside. This is also gone. And now the calculation looks like 2 minus 1 is 1, 1 minus 1 is 0. And then we have 1. Sort again in the non-increasing format. Easy. Again, the first element dictates take 1 chocolate outside from the next element. So this is gone. After dictating, he is gone. And the sequence calculation looks like 1 minus 1 is 0, and then we have 0. If final result is all zeros in the degree sequence, this means your simple graph can be made. If that is not happening, then simple graph cannot be made. Okay. Otherwise, the simple graph cannot be made. For this question, simple graph can be made. So I hope now you will understand the 𝐏𝐻𝐃𝐑𝐦 theorem, what I have written here. This theorem tells which degree sequence belong to the simple graph. Basically, degree sequence can be converted to simple graph or not. Okay. So this theorem helps us for this kind of question. What is the theorem? First step, arrange the degree sequence in the non-increasing order, which is nothing but the decreasing order. Okay. Second step, remove the first element. Remove the first element and he dictates, like the first element dictates, you have to take 3 chocolates outside from every element such that every element is giving 1 chocolate. So minus 1, 3 chocolates are out. Now you do the calculation. That's what I'm writing. So subtract 1 from the next element till minus 1 value reaches minus d. So which basically means do minus 1 up till all the chocolates are taken outside. And if the third step is done, do the calculation and then arrange the degree sequence in non-increasing format again. See, after doing the calculation, we arranged again into the non-decreasing format. And then what we have to do, repeat the process. So we repeat the process, dictated, calculation, sorting, dictated, calculation, sorting, till the end where you see all the entries is 0, then you can say that it's graphical. We can make simple graph. Otherwise, it's not graphical. We cannot make the simple graph. So do we have any example? I do not know. You can try this big question by yourself. Tried? Now it's my turn to solve the question. Okay. So the very first step is this. In the non-increasing format, answer is yes. So if that is the case, then the first element will dictate. What it will dictate? 4 chocolates outside. So minus 1, minus 1, minus 1, minus 1. Calculation becomes 3, 2, 2, 2, 2, 2. Now check. Is it sorted or we have to sort? It is sorted, non-increasing sequence. So again dictate, first element dictate, take 1 chocolate outside. And if you do the calculation now, you will see 1, 1, 1, 2, 2. But this is not non-increasing format. Rearrange. First element dictates minus 1, minus 1, Okay, so after dictating you can just do the cancellation just for in case to make your things pretty easy to write the next step. So 2 minus 1 is 1, 1 minus 1 0, and now again it is not in the sorted version, so sort it in the non-increasing format. First element dictates, calculation, sort it again, first element dictates, but if you do now you will get minus 1, and negation is not allowed, right? All entries should be 0, it should not be negative. So our last conclusion is this is not all zeros. If we do further calculation we will get negative degree cannot happen, so we fail to get all 0. If we fail to get all 0, the given degree sequence cannot be converted into simple graph. Understood how beautiful this theorem is? If understood, so I have solved your biggest problem, and now we can move forward for the special graph topic. So we have different types of graph, we say it as special graph, and this different types of graph is for a specific subset. You have seen graph had two types, directed graph, undirected graph. In that undirected graph we had three types: simple graph, then we had a multigraph and pseudo graph. Now this lecture is based on all the special graph of this simple graph. Okay, so all these are simple graph, which means no self loop and no parallel edges. Now we have 6 types. I know it's very much like boring, sir, 6 graph, but it is very interesting. It's very simple. The name will give you the idea, and then we will do analysis so that we can solve the gate questions. Okay, so the very first graph we have is a null graph. The name says null, which means null edges, no edges, only vertices. That is our null graph. Symbol, you can say it as null starts with n, so n. What is this small n? Number of vertices. Or you may say in matrices we represent null by phi, so phi n. What is n? Number of vertices. Okay. Now before going to this, let me show you some example. Suppose I have n is 0. N is 0 means 0 vertices, that cannot happen, so n should be 1. Therefore I am writing number of vertices should be minimum 1. Okay, so when n is 1 vertex, that's it. This is our phi 1 as per the symbol. This is the null graph, can be represented as phi 1. Number of edges is 0. Okay, for any null graph number of edges is 0 because only vertices. Null graph means no edges. No edges means number of edges is 0. I hope this part is pretty much clear, and if that is clear, then n is 2. How it will be represented? 2 vertex, but all of them are isolated. If you try to join them, then it is no more null graph because now we have edge. Null graph means no edge. So this is our null graph of 2 vertex. You can change the orientation like this also, I have no issue. Okay, or you may write in this way, any way you can do it. N is equal to 3 like this. Orientation, if you want straight line like this, you can do any way. All of this graph are nothing but the null graph of vertex 3. Understood? Easy. So phi 1, 1 dot, phi 2, 2 dots, phi 3, 3 dots, and these are all our null graph, no edges. Going to the second graph, regular graph. What is a regular graph? Sir, we have seen this in the previous lecture, when the minimum degree and the maximum degree are same, which means every vertex is having same degree. So we say it as regular graph. Okay, it's like regular day, same day again and again, so same degree again and again for all the vertex. Correlate with the real life, correlate with the simple meaning, you will understand. So regular graph means regular degree, every degree is same for all the vertex, which means small delta, capital delta is equal to k, and we say it as k regular graph because if you have 0 degree, that can happen. 0 degree, yes, isolated vertices. Isolated vertices says that no one is coming to me. If no one is coming to you, you have 0 degree. So k is equal to 0. Always remember what is this k? This k is not the vertex. This k is the idea of degree because minimum degree, maximum degree is k, right? So this k is nothing but the idea of degree. So when someone says k is 0, this means 0 degree regular graph. 0 degree regular graph means isolated vertices. It can be 1, it can be 2, it can be 3, it can be 4, it can be n isolated vertices. So this is nothing but the null graph. We have seen null graph means isolated vertex, which means null edges, no edges. So we can say, sir, this is nothing but phi n graph. Yes, you can relate. You can relate. But can I say all the regular graphs are the null graph? No. I cannot say all the regular graph are the null graph, but I can definitely say all the null graph is a regular graph. See, all the null graph, you make any null graph, it will always have what? Same degree, which is degree 0. And if it has same degree for all the vertex is a regular graph. So all the null graph is a regular graph, to be very specific, 0 regular graph. But all the regular graphs are not the null graphs. Or any example, next example, take k is 1, you will see edges now. If you see edges, it cannot be null graph then. Okay. So when k is 1, it means degree is 1. If I am a vertex, I will always have degree 1. When it can happen, see, 2 vertices, 1 edge. What is the degree? Degree of all the vertex is 1. Sir, can it be like this? Yes. But sir, these two are not connected, these two are not connected. Yes, disconnect graph is also a graph, therefore I can make. Is it following the definition of simple graph? Definitely, we do not have parallel edges self loop. If that is the case, then some vertices not connected is okay. Okay, but this can be again considered as what? It is considered as a regular graph, because this vertex is having degree 1, this vertex degree 1, all the vertices are having degree 1. So this is 1 degree regular graph, or you can say simply 1 regular graph. Understood? If k is 2 means 2 degree for all the vertices. So 2 regular graph. So you can see the example. This is the example. This vertex have 2 degree, 2 degree, 2 degree. This is having 2 degree, 2 degree, 2 degree. But what if someone join the diagonal? Now this is no more 2 degree. See, this is having 3 degree, this is having 3 degree. So all the vertex is not having the same degree. If you join like this, then you can say, is this a regular graph? Yes, because 3 degree, 3 degree, 3 degree, 3 degree, all of the vertices is having degree 3. So this is what? A 3 regular graph. Understood? So for all vertices, if degree is same, then that value regular graph it is. Very simple. Understood? So I won't waste much time. Just I will give you all the connects and the logics and the contra statements so that you understand it very well. So now we have 3 notes based on the regular graph. The very first note is, suppose you have k regular graph, then minimum number of vertices are how much? Check. 0 regular, you can see 1 or more vertex. Okay. So minimum you should have 1 and maximum it can be anything. So if 0 regular, then 0 plus 1 is the minimum vertex. If I have 1 regular, then number of vertex minimum, see 2, here we have 4, again we'll have some more, right? So here I can say 1 regular means minimum vertex should be 1 plus 1, 2. Here 2 regular, how many vertices? 3, 4, so minimum 3. So if 2 regular, minimum is 2 plus 1. So if k regular, minimum number of vertices is k plus 1. Now some students might be thinking, sir, can I say if I have n vertices, then the degree is n minus 1. See, if I have 3 vertices, the degree is 3 minus 1. If I have 2 vertices, the degree is 2 minus 1. If I have 1 vertex, the degree is 1 minus 1. Can I say like this? Answer is no. Why? 2 vertices, degree is not 2 minus 1. Check. 4 vertices, degree is not 4 minus 1. Understood? So n vertices, degree is n minus 1, or it is k regular graph is not allowed. This I have proved. Okay, understood? So this was the first point, that only you can say if you have k regular graph, then the minimum number of vertex, we cannot say exact, we can say the minimum number of vertex is k plus 1. This is necessity. Second point is, if k is odd, you know very well, we have seen the proof. K is odd means, k is what? Sir, k is degree of all the vertex. If it is odd, degree of all the vertex is odd, then the counting of those degree will always be, the number of vertex of that will always be E1. Yes, you can check also. Degree odd this thing, then the number of vertex E1. Okay, number of vertex is E1. Check, the number of vertex is E1. Do we have any other example? Yes, you can create, right? You can create, suppose I join the diagonals. If I join the diagonals, can I say by joining the diagonals, now every vertex is having degree 3. So this is 3 regular graph. Yes, this is 3 regular. So if it is 3 regular, then tell me degree is odd. So can I say the counting of vertex is E1? Yes, 1, 2, 3, 4. That's what I have written. If degree is odd, then the counting of vertex is E1 only. It cannot be odd. You can try. Now the third point is regular graph may or may not be connected, which you have seen. Vertices may or may not be connected. So regular graph may or may not be connected. Understood? Everything is clear. So keep that in mind. Regular graph means regular degree. Every degree of all the vertex is same. That's all. Okay. Now to the third graph. That is a complete graph. The name says complete. No one is left behind. Every vertex is joined with every other vertex. No one is left behind. I am friend with everyone. Complete graph. Complete family. Complete friends. Okay, so if every vertex in G is connected to every other vertex in G, then we say it as complete graph. Notation is Kn. Okay, notation is Kn. Always remember the notations. Here it was K regular. Previously we had phi n. Okay, previously we had phi n. Here we had K regular graph, and now we are having Kn. So obviously there is some connection between K and Kn. We'll cover that also, but for now, for notation purpose, remember complete graph is Kn. What is n here? Number of vertex. So if I have 0 vertex, so 0 vertex not possible. 1 vertex should be there. So 1 vertex, can I say that 1 vertex is there and it is a complete graph? Yes, he cannot talk to anyone, so he is isolated himself only. So yes, it's a complete graph. So what is this, sir? This is nothing but a null graph of phi 1. Absolutely. Or you may say it as 0 regular graph, just connecting to the previous graph. This graph we have seen in the null graph when n was 1. This we have seen also when we were studying the regular graph, and for regular graph when the degree was 0. So 0 regular graph, right? So you can say this thing is null graph of n1, 0 regular graph, and in fact the complete graph. So this thing is everyone right now. Okay, null, regular, complete, everything. But this thing, when I say n is 2 means 2 vertices and everyone is connected to each other, like all the vertex are connected to every other vertex. So you can see that this is the graph, but now this is not the null graph. So this graph is not the null graph. Is this a regular graph? Yes, I can say it is a regular graph because degree of this vertex is 1, degree of this vertex is 1, every vertex is having same degree. So 1 regular graph. And for this topic, complete graph, we can see it as K2 because in general the notation is Kn for the complete graph. So 2 vertex like this, 3 vertex like this, 4 vertex like this. You can check. If I keep 3 vertex, every vertex connected to every other vertex. Isn't it? 4 vertex, every vertex is connected to every other vertex. Okay. So this is your complete graph. Every vertex connected to every other vertex. And if you write K3, 3 vertex, K4, 4 vertex, you can also say this graph, sir, it resembles degree 2, degree 2, degree 2, 2 degree regular graph. This is degree 3, degree 3, degree 3. So this is 3 regular graph. Yes. So can I say complete graph is connected to regular graph and all the complete graph is regular graph and all the regular graph is a complete graph? Can I say like this? Two-way theorem? No. No. For now you can say a one-way theorem that all the complete graph is a regular graph. Obviously, all the complete graph is coming out as regular graph, but all the regular graph is not the complete graph. Do you need one example? Check. Vertex degree 2, degree 2, degree 2, degree 2. So all the degrees are same for all the vertex. This means it's a 2 regular graph. but it is not a complete graph because every vertex is not talking to every other vertex. See, this is missing. This thing is missing. So every vertex is not talking to every other vertex. Therefore, this is not a complete graph. So here you see a contradiction that it was a two regular graph, but not a complete graph. So I hope this conclusion is clear that complete graph is definitely a regular graph, but regular graph is not necessarily a complete graph. Okay. This conclusion is clear. Also, you may note that when I say it's a n is 4 vertex complete graph, then the regular version is 4 minus 1. Here, if I say 3 vertex complete graph, then the regular version is 3 minus 1, and so on and so forth. So if I have kn complete graph, then in the regular graph version, it would be n minus 1 regular graph. Okay, just by the observation, I have come up with this thing. Clear, easy. Now the second thing is size of Kn. What is size of Kn? Since Kn says every vertex is connected to every other vertex, it's like the combination. You have n points, join every one. So from n points, select 2, you will get nc2, which is n into n minus 1 by 2. That is your size of Kn. So what is size? Size means the number of edges. So number of edges for Kn, it would be maximum number of edges because every vertex is connected to every other vertex. So we have to find the maximum number of edges. Maximum number of edges is nc2, which is n into n minus 1 by 2. Very simple with the combination, or else you can use the handshaking theorem. Already explained this in the previous lectures. But I guess the third topic is crystal clear. That was our complete graph. Moving to the fourth graph, cycle graph. As the name suggests, we have to move in a cycle. Okay. So what we have to do? First, draw the vertex and then move in a cycle. That's all. See, cycle graph, since it starts with C, the symbol is Cn. But if you want to make a cycle, minimum you should have 3 vertex. You can't make cycle from 2. Check. Can you make cycle? No, it's a straight line. It's not a cycle. Cycle means close, but this line is not close. If I have 1 vertex, can I say a cycle? No. 2 vertex, can I say a cycle? No. 3 vertex, yes, you can make a close figure. If it is close, we can say it's a cycle. So join, join, join. Like this, you have to join and you will see a graph. You can make as a triangle or anything because shape doesn't matter. Joining matter. That's what computer need. The maths calculation, the set of vertices and edges, that's what he need rather than the shape. So I hope the cycle graph idea is pretty clear. We should have a cycle. It's a closed figure. Because it is a closed figure, vertex should be minimum 3. Symbol is Cn, and how to draw it? First draw the vertex and then connect the graph. You can see C3, 3 vertex, 1, 2, 3. Now start from here, join, join, join. Cycle graph. Okay, C4, 4 vertex, join, 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 join. Cycle, done. 5 vertex, 1, 2, 3, 4, 5. Join, 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 join. Cycle complete. So C5. Easy. Now if you see carefully, this cycle graph is again kind of like a regular graph. See, vertex is having 2 degree, 2 degree, 2 degree. Every vertex is having 2 degree. Here every vertex is having 2 degree. Here every vertex is having 2 degree. Oh, so in a cycle graph, in general Cn, we can say it's a regular graph of degree 2. So 2 regular graph I can say just by the observation. Understanding that every cycle graph is a 2 regular graph. You can see by the observation. Now I have a question for you. If you observe again, what you will find is 3 vertex, 3 edges, 4 vertex, 4 edges, 5 vertex, 5 edges. So can I say number of vertex is number of edges? If that happens in any graph, I can say it as a cycle graph. And vice versa, I can say if it's a cycle graph, then this should happen. Tell me. Pause the video, think. Can I say it's a two-way theorem? Whenever this kind of question comes in the GATE exam or any exam, you have to just think of counter examples. Okay, rather than proving it mathematically, find some counter example. So here we have observed whenever I drew a cycle graph, I always got this thing. So this way is 100% true. You can see from the example. Cycle graphs I have drawn, and from that I have concluded that 3 vertex, 3 edges, 4 vertex, 4 edges, 5 vertex, 5 edges. So that way is true. But if this thing is happening, can I see a cycle graph? No, may or may not be true. That is the answer. Sir, why? See, I have 4 vertex. I have joined the edges like this. Is it valid? Yes, it's valid. But now, vertices 4, edges 4, but it is not a cycle graph. That's what I was saying, that if this thing is happening, then may or may not be cycle. But if it is a cycle graph, definitely, see, is this a cycle graph, closed curve? Yes. Okay, closed curve, cycle graph. And can I say now number of vertices, number of edges? That is 4. Yes. Please make a note. Some student will like, sir, what if I join this? Then this is not a cycle graph. Cycle graph means only cycle you should make. You should not make extra stuff. Okay, just cycle you should make. You should not make extra stuff like the diagonals and other thing. Okay, so cycle graph, I guess each and every scenario is seen. Counter examples, the doubts, everything is clear. Now moving forward for the 5th type, that is a wheel graph. Name is saying wheel. As you move forward in the number of vertices, your graph would look like a wheel. As simple as that. Okay, so wheel graph starts with W, symbol is Wn, and for a wheel, again, minimum vertex should be greater than 3, because wheel says one thing is you have a cycle and then you have a vertex at the center, and that's how your wheel looks like in a car, in a bike. So cycle plus vertex at center. Okay, so cycle plus vertex at a center. So that's what this concept is all about. Wheel graph is basically connection of two things, cycle graph plus vertex at the center. Since wheel starts with W, so symbol is Wn, n should be greater than 3, because for cycle n was minimum 3. Since you are adding one more vertex at the center, now the minimum became 4. So you can say it as, this thing is nothing but n is greater than equal to 4, because cycle minimum was 3 and then you added vertex at the center, so it's 3 plus 1, minimum 4. How to draw it? Make cycle first of n minus 1 and then insert vertex at the center and connect to all the vertex. That's all. See how to do it. If I want to draw W4, what I will do? I will first make Cn minus 1. Okay, so Cn minus 1, you can see 4 minus 1 is 3 vertex. So 1, 2, 3, join them. Join, join, join. Okay, so first step is done. Second step is insert vertex at the center and now join with the every other vertex. This is our wheel graph. Yes, this is our wheel graph. Very easy 2-step process to develop the wheel graph. Suppose someone is saying n is 5. How to do it? Let me erase this. N is 5. How to do it? First thing is make cycle. Cycle of how many vertex? N minus 1. So 5 minus 1 is 4. 4 vertex. Draw the cycle. Connect, 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 connect. Now vertex at the center. Join with the every other vertex. Easy, done. This is our wheel graph made from cycle of n minus 1 vertex and vertex at center. Okay, from that we have created. Now please observe carefully. There is some interesting point in this. Similarly, you can create W6, W7. Eventually, as you move forward, you will see a wheel. Okay, eventually you will see a wheel as you move forward in the number. Nevertheless, there is a great observation here. If you have seen, if you have noted, that in this graph we can see vertex is having degree 3, this vertex degree 3, this vertex degree 3, this vertex degree 3. Oh, so for all vertex degrees 3, so it's a 3 regular graph. Okay, and it is the only regular graph in Wn. In whole wheel graph, this is the only graph which is having a regular graph format, and that too 3 regular graph. Other graph you make of wheel, you won't get. Check this. Degree 3, but here degree 4. Not all vertices having same degree, so it's not a regular graph. Similarly for W6. Okay, the center will have more degree and that would be the problem for a regular graph. Okay, so I hope this part is clear. Now if someone asks you about the number of edges in the wheel graph, how to comment? See, wheel graph is made from 2 things. So with the help of that, we can comment on the number of edges. Number of edges is the number of edges in the cycle plus number of edges through this center vertex. So number of edges in Wn is number of edges from the cycle. Cycle was made from n minus 1 vertex. If you have n minus 1 vertex, then you remember, if it is a cycle, then it is definitely number of vertex is number of edges. So n minus 1 vertex will give me n minus 1 number of edges. So that's the thing I have written here. Easy, clear. Now this center vertex is connected to how many points? n minus 1. See, n minus 1 points, because n minus 1 vertex was used to make cycle. Therefore n minus 1 points. Okay, so this thing is connected to 3 points, which is 4 minus 1. This thing is connected to 4 points, which is 5 minus 1. So that n vertex, that center will be connected to n minus 1. Okay, that n minus 1, I should not write the n vertex, I should write the center vertex, to be very specific. Center vertex, that center vertex will be connected to n minus 1 points, so n minus 1 edges, and therefore your complete number of edges in Wn is n minus 1 plus n minus 1, which is 2 times n minus 1. Easy, understood, simple. Okay, to the last graph of the today's lecture, which is n cube graph. As the name suggests, n cube. So you might be thinking, oh, n cube means n cube. No. Okay, he is giving the idea that eventually it will form a cube. Okay, it will be like a cube structure. N cube says like this. It is not like n to the power 3. So first thing, the symbol is Qn. Now please make a note, this n is not the number of vertex. Up till now, whenever you have seen the subscript n, it was number of vertex, isn't it so? Yes, but here this n is not the number of vertex in n cube. So if n is not the number of vertex, then what is number of vertex? Number of vertex is 2 to the power n. Now you will remember, oh, 2 to the power n. This is the sublattice question we have seen. Exactly. And therefore the number of edges will look like n into 2 to the power n minus 1. If you try to join, it would be n into 2 to the power n minus 1. I hope this part is pretty much clear. The symbol is Qn, that n is not the number of vertex. The number of vertex is 2 to the power n, and the number of edges would be n into 2 to the power n minus 1. Let us see the example. When n is 0, it is Q0. So number of vertex would be 2 to the power 0, which is 1. Number of edges would be, when you have only one vertex, no need to do the calculation. Obviously, it would be 0 edge. When n is 1, it is Q1. So when n is 1, the number of vertex is 2 to the power 1, which is 2. So 2 vertex. 2 vertex, and then if you need the number of edges would be n into 2 to the power n minus 1. So 1 into 2 to the power 1 minus 1, which is nothing but 1. So only one edge you will get, and obviously you cannot get the multiple edge, because this is again a simple graph and you cannot have the self loop and the multi edge, right? So these things are not possible. Even if you do not do this calculation, simple concept you can make like this. What about the Q2? Q2 have various possibilities like this also, but you should not make that, because the concept says number of vertex is 2 to the power 2, 4. So yes, 4 vertex. Number of edges is n into 2 to the power n minus 1. So 2 into 2 to the power 1, that is 4. So 4 edges like this. Understood? Now your question might be, sir, can I make the 4 edges in this way? No, you cannot make 4 edges in this way. You have to connect in a form of a cycle only. Okay. So in short, your framework should be like a cube. So is the base structure of a cube, right? Q2 looks like a base structure of the cube. And eventually if you go to the Q3, you will get a cube. As you can see, if Q3 is there, then number of vertex is 2 to the power 3, which is 8, and number of edges is n into 2 to the power n minus 1. So how much? 3 into 4, 12. So you can see here we have 8 vertices. Can you see the 8 vertices? And then if you join, because joining has various ways, you can join like this also, you can join like this also. You should not join like that. You should join in such a way that it forms a cube. Okay. So that kind of joining you have to do. If you do that kind of joining, you can see that ultimately we get a cube, and this is our n cube graph. Easy. That's it. I hope everything is crystal clear and you have no doubt. in all the graph. I have connected, I have explained in all the variations, the traps, the one-way theorem, the two-way theorem, everything I have explained, and also this powerful theorem, 𝐏𝐻𝐏𝐃 theorem. That's it for today. Thanks for watching the lecture. Welcome to lecture 4. In today's class, we are going to study some more special graph like bipartite graph and complete bipartite graph. But before going to those topics, first let us understand what is independent set. See, we have a definition for sure, but before going to the definition, let us understand some example. I have one simple example, a graph which has 3 vertex A, B, C. Suppose they are connected like this. Okay, then tell me set of all vertex. It would be A, B, C. This is set of all vertex, right? Now, independent set is a set made from vertex such that if you pick any 2 vertex, this thing, then they should not be connected to each other, which means there should be no edge between them. If that is happening, then that set is known as independent set. Understood the simple definition? If yes, then tell me, suppose I have a set P which has the vertex AB. Can I say this set as independent set? No, sir. See, A and B are the vertex, but they are connected to each other. There is edge between them. If there is edge between them, then they are dependent. They are not independent. Therefore, this set is not independent set. Understood? This set is not independent set. Suppose I have A, C. Can I say this set as independent set? Yes, sir, because vertex A and vertex C, they are not connected to each other. They are not connected to each other. There is no edge between them. Therefore, this is independent set. Okay. Suppose I have a set like this, single vertex. Can I say it as independent? Yes. Every single vertex set is independent set. Understood? Now, suppose I have this set V. Can I say this as independent set? Now you will say, sir, A and C, see, no edge between them. But AB, there is edge between them. BC, there is edge between them. If you get any one case where there is edge between them, then this complete set is not independent set. Understood? Independent set means you take any 2 vertex and there should be no edge between them. But here, there are some pairs where we get edge. Therefore, this is not independent set. Now, I guess you understood the definition crystal clear. A set of vertex V is called independent set when any 2 pair of vertex in V do not have edge between them. Simple. So, try this question by yourself. This is the graph. A, B, C, D are the vertex. We have sets V1, V2, V3. Find which among them is independent set. Tried? Okay. If you see carefully, single sets are always independent set. AC, A is here, C is here, no edge between them, independent set. ACB, BC will talk to each other because there is edge between them. If you get any case where there is edge between them, then not independent set. Understood? Okay. Now, going to the next topic, which is bipartite graph. Now, please make a note. If I straight away read the definition, a lot of students will say, sir, I am unable to understand anything. So, I won't do that. I will make things very, very simple, like always. So, let us see the title, bipartite graph. What it says, bi means 2, partite means partition. So, you will do partition and create into 2 stuff. But what to partition? In graph, you have only 2 entities, vertex and edges. Obviously, you cannot divide the edges, you cannot cut the edges, but you can cut the vertices. So, you have a vertex set, you will cut it into 2, and that is nothing but the bipartite. Now, let me go deep dive into the vertex set. Suppose V is the vertex set of the graph, so it will contain all the vertices. What's your task is to partition it into 2 set P and set Q. Sir, what's unique about this set P and set Q? First uniqueness, they cannot be empty. They are non-empty set, which means at least one vertex should be present here and one vertex should be present here. Okay, that is the first important thing. Second important thing is they should be disjoint, which means if I get vertex A here, then there cannot be vertex A here. They should be disjoint. There should be no common vertex in both. Okay, no common vertex. Similarly, if Q set has the vertex B, then P set cannot have the B vertex. Okay, they should be disjoint. This was about the vertex. Now comes condition on the edges. If edge is present, then that edge should connect in a way that it will take one vertex from P and one vertex from Q. Like this connection is possible in bipartite, but this connection is not possible in bipartite. Basically, if there is edge, then that edge should be connected with a condition. What is the condition? One vertex from P set, one vertex from Q set, and you are connected, that edge is allowed. But what if one vertex from P, one vertex from P, connect edge, not allowed in the bipartite graph. One vertex from Q, one vertex from Q, connect, not allowed in the bipartite graph. Understood? So basically, this three criterias you have to keep in mind. If that three criterias are satisfied, then that graph is a bipartite graph. So I repeat, bipartite means partition to make two, but what partition? The vertex set is partitioned into two set P and Q such that this set P and Q have vertices, at least one vertex, so they should be non-empty sets, and this P and Q should be disjoint set, no vertex should be common between them. And the third thing was on the edges. If edge is present, then the condition is that edge should have one vertex from P and one vertex from Q. It cannot be like edge is having vertex from P and P or edge is having vertex from Q and Q. That is not allowed. Easy. Now you understood the bipartite graph. If yes, then these are the simple note which you have to keep in mind. Set P union set Q would be V. Obviously, suppose I should not do this, but I got no option. Suppose I have this vertex P, I did the partition. Okay, P set and Q set. Now if I join it, I will get the original paper back. I will get the vertex V back. That's what this first statement meant, but I just cut my paper, which was very important. Nevertheless, this lecture is very important for you guys, so focus here that P union Q set should be again back to the original vertex set V, which is of the graph. Second thing is disjoint stuff. P intersection Q should be null, no vertex should be common. Understood the first note. Second note is no self loop allowed in bipartite, no self loops are allowed. And very obvious, if you have P and Q, any vertex here, if you try to make self loop, then that criteria is not matched. Edge should be such that one vertex from P set, one vertex from Q set. But if you make self loop, then both the vertex from the same set, and therefore it will not be valid in the bipartite criteria. So it's invalid in the bipartite criteria. Therefore, no self loop in the bipartite. Third thing, P and Q are independent sets. Now you will realize, sir, when you told the definition about the edge condition, that if edge is present, then it should be such that that edge has one end, one vertex in the P set, other vertex in the Q set, and no edge will have vertex from P to P or Q to Q. That is nothing but the definition of the independent set. Isn't it so? A vertex V is called independent set when any two pair of vertex in V don't have edge between them. Don't have edge between them. So all this vertex won't have edge between them. All this vertex won't have edge between them. So can I say P and Q are basically independent set in itself? Yes. Therefore, to understand that independent set, I just gave you the basics first. Now I hope you have understood all the criterias of the bipartite graph. Basically, there are two criterias. What is the criteria? Vertex into two set, P set and Q, they should be independent and they should be conditioned. If these conditions are satisfied, that graph is bipartite. That's how the questions are framed. if a graph is there, tell me whether it is bipartite or not. So this is the process. To understand this process, we'll take example and then we'll go back to the algorithm. So this is the example. We have a graph. Can I say it as a bipartite? To find it is bipartite or not, the step number 1 is we need the vertex set. So write all the vertex in the graph A, B, C, D, E, F. Second, bipartite means partition into 2 sets PQ such that they are independent sets, and P union Q should be the vertex set, P intersection Q should be the disjoint null. Okay. Now, how to write the P and Q set? There is a trick. The trick is, first choose any vertex you want. I will choose vertex A and write in the P set. Now this vertex A has edges which is joined to some other vertices like F and B. If I write B and F here, then this set P is not independent set. Therefore, this B and F should be written where? Should be written in the other set. This is the trick. Then we can say edge is present between A and B, but A is in P and B is in Q set. So see, no independent set criteria is harmed, which means there is no such edge which is having vertex from P to P or vertex from Q to Q. Understood? If I wrote BF here, then the edge will have vertex from P to P, and that won't make it independent set. I hope this part is pretty much clear. This trick is pretty much clear. So A, B, F vertex are done. Now focus on the next vertex. So we have C vertex. Where to write? Will you write C here or C here? If I write C here, will it be okay? No, because then CB edge is there. That would be a problem, and therefore it won't be independent set. So C is written here. A, C, are they talking to each other? No, they are not talking. So they are independent. Okay, if C is written, then C is connected to B. B is already written in the Q set. C is connected to D. That D should be written here. So C, D is done. Now talking about E. E should come where? Here or here? E cannot come to the Q set because there is edge between E and D. So E will come only to the P set, and we are done. Now you can verify also A, C, E. Okay, there is no edge between them. B, D, F, there is no edge between them. So yes, we have successfully partitioned the vertex set into 2 such that they are independent sets like P union Q is what? P union Q is equal to V and P intersection Q is equal to null, and also edges criterias are justified. So this is the process. Choose a vertex V, choose a vertex anything from V and write in P set. All the adjacent vertex to it write in Q. Okay, so this were the adjacent vertex B and F, write in the Q. Now select another vertex from V which is independent in P, like there should be no edge between them, and repeat the process. If you do that, the edges criteria are satisfied. Now check P union Q is equal to the vertex set. All the vertices are there, and also check the intersection is null. So yes, if it is there, then bipartite, otherwise not. If you have understood this process, try the next question. Okay, pause the video, try. I hope you have tried. Let me also explain that if you want to convert this in the form of the bipartite graph, what you can do is write the vertices of the P set here, write the vertices of the Q set here, and just follow the edge style. I can do it. See, the P vertex was A, C. The P set had the vertices A, C, E, and the Q set had the vertices B, F, D. Now just follow this structure: A to B, A to B, and then B to C, B to C, then C to D, C to D, then we have D to E, then we have E to F, then we have F to A. So this way you can create the graph. As you can see, the partition is crystal clear. Easy, understood? Nevertheless, the question was whether this is a bipartite graph or not. I hope you have tried. The answer is, sir, this is not a bipartite graph. Why? Because the vertex set was A, B, C, D, E, and then split into the two sets such that they are independent. So take any vertex, let me take A. All the adjacent vertices like the edges connected to B and C, these are the adjacent vertices. Right to the next set, BC. Okay, so A is gone, B is gone, C is gone. Now D. D will come here or here. D cannot come here because DB is connected. See, DB is connected. So D cannot come here. D will come definitely here because AD is not connected. Okay, so D is done. Then you will say D adjacent is E, D adjacent E right here, and we are done. The answer is wrong. You have to check there should be no edge between any two pairs in this set, then only this P and Q are independent. If you see carefully, then you will find E is connected to B, E is connected to B, E is connected to B, therefore E cannot be written here. Can E be written here? No, E cannot be written here because E is connected to D. So E cannot be written. These are the only independent set, but that criteria P union Q is not equal to V nav because E is missed, and therefore we will say that this is not bipartite graph. Understood how to figure it out whether this is bipartite graph or not? So very simple. I just told you independent sets P and Q and then this criteria checking. So this is how you can figure it out. Now there are tricks. I know doing this manual checking will be a very time taking process. So is there any tricks and techniques? Definitely. The first trick is whenever you see triangle shape, then straight away say no bipartite. Have you seen the triangle shape here? Yes. So straight away no bipartite. Are you seeing triangle shape in the first example? No. Then it may be a bipartite graph, but if there is a triangle shape, definitely there is no bipartite. Okay, this is the first trick. The second trick is if you are dealing with cycle graph, then cycle graph is bipartite if and only if n is even, if the length is even, if the number of edges is even, then you can say yes, Cn is bipartite. Like here, this was a cycle graph. Yes, number of edges 1, 2, 3, 4, 5, 6, even. Okay, cycle graph even, always it is bipartite. No need to check, no need to do all this calculation. Understood the two trick? If yes, try these questions. I hope you have tried. The first question, we have a cycle graph and number of edges is even, so definitely a bipartite. This thing, is it a cycle graph? No, because we can see here line is drawn. Okay, so this is not a cycle graph, that trick won't work, but we can see a triangle. So if there is a triangle, then definitely it is what? It is not a bipartite. Triangle shape, not a bipartite. Triangle shape, not a bipartite. Triangle shape, not a bipartite. Wrong. Now I know a lot of students will say, sir, this is cheating. In the previous slide itself, you have told that if triangle shape is present, then definitely not a bipartite, and we can see a triangle shape, then therefore it is not a bipartite, and you are saying it is a bipartite. Reason is when I say there is a triangle shape means vertex present here, vertex present here, vertex present here, and a triangle shape is formed. Can you see vertex at the center? No sir, there is no vertex at the center. If there was vertex at the center, then yes, a triangle shape, then it is not a bipartite. But since there is no vertex at the center, therefore there is no triangle. If there is no triangle, then it's a bipartite graph. You can verify. I will split into the two set. Let me start our set P with this first vertex E. Adjacent vertex are F and D written in the other set. So E is gone, F is gone, D is gone. Now A vertex should not be with F, so should not be with this, so should be with the P. Now adjacent vertices are F and B. B can be written here. So A is gone, B is gone. What about C? C connected to D, C connected to B, so C is connected to B, it cannot be written here, so C should be written here. I have done the splitting. You can check EAC, are they independent? EAC, yes, no edges between them. FBD, are they independent? Yes, because no edges between them. So I have successfully splitted into the two independent set where union of P and Q is the vertex set and intersection is the null set. So definitely a bipartite graph. Understood? And final example, we have a cycle graph, but 1, 2, 3, 4, 5, odd cycle, so not a bipartite. I have told you the trick. So if Cn is present, check the length. If it is even, definitely bipartite. If it is odd, like this, not a bipartite. Easy, understood the trick. If understood the trick, then we can go to some important keynotes. Now the first note says smallest bipartite graph G will have two vertices only. Very obvious. See, if I have one vertex, then how can I split into the two vertex set which are non-empty? Either A can come here or A can come here, right? So if A came here, then Q will be empty set, and empty set should not be present in the bipartite graph. So one vertex graph cannot be the bipartite. Two vertex graph can be bipartite because very simple. Vertex set is AB. You can make P and Q set. See A here, B here, and yes, edge is made such that one vertex is in P set, one vertex is in Q set, and secondly, P union Q is the V set, P intersection Q is the null set. Okay, so we can say the smallest bipartite graph will have two vertices. But sir, can a null graph be a bipartite graph? Null graph. See, null graph with one vertex cannot be a bipartite graph, but null graph with two vertices can be a bipartite graph. And you might be thinking, but sir, in every example we got edges, there were no isolated vertex. Yes, I agreed, but in the definition I have told you, if edge exists, then this should be the criteria. If edge exists, so this means if edge is there, then that criteria, but if no edge, no criteria, right? So if I have null graph like this with two vertices, this is definitely a bipartite graph because I can make set P having this vertex A and set Q having this vertex B, and all the criteria are satisfied. P and Q are independent sets. P union Q is the vertex set. P intersection Q is the null set, and edges criteria is also satisfied. If edge present, then the condition, but here no edge, so no condition. So everything is matched, bipartite. So remember, edges may or may not be present in the bipartite, and still we can say if no edges are there, we can say it as a bipartite. So yes, phi 2 is a bipartite graph. Understood? Third point, Kn. Do you remember Kn previous lecture? Yes sir, this is a regular graph, right? Wrong. This is not K regular, this is complete graph. Yes, Kn means complete graph where n is the number of vertices. So Kn, complete graph with n vertices, is bipartite only for K2 when there is two vertex. Apart from that, no complete graph is a bipartite graph. Do you want to see the analysis? See, K1 cannot be a bipartite for simple reason. We'll get one set which would be empty set. K2, you have seen, this is a bipartite graph, already explained. For this smallest bipartite G will have two vertices, that is your K2 only. And then you will see the complete graph 3, and then we'll get a problem. 3 vertex ABC. Definition of complete graph, every vertex is joined to every other vertex. So you can see a triangle. Triangles are not bipartite. K4 A, B, C, D. So now connect. Stop. I know you can connect more and more and more, but you can see that triangle is formed. So not a bipartite. So K5, K6, everything would be just add-on of the K3, right? Just the add-on in the graph. and therefore we're going to say that the complete graph, if I leave K2, the whole history of the complete graph, if I leave K2, that whole history would look like a not a bipartite graph. Okay, so I hope everything is crystal clear right now. All these 3 points, you have no confusion. Generally students have confusion because edges may or may not be present, are not present in your books. So I wanted to clear that concept as well. So in a bipartite, edges may or may not be present, and if you have a complete graph, then in that only K2 will act as a bipartite, others won't. Clear? So bipartite graph is done. We are moving forward for the last concept of today's lecture, which is complete bipartite graph. Now please make a note, complete bipartite graph would be extension of the bipartite graph. So recall, what is a bipartite graph? Partition of the vertex set into two sets, P and Q. These two sets are independent set. Criteria: P union Q should be vertex set, P intersection Q should be disjoint set. You have studied this. I hope a lot of time repetition we have done. Now it's crystal clear register. So what is new in this complete bipartite graph? The new thing is, whenever you see complete, remember the complete graph from the previous slide, edges. Every vertex is connected to every other vertex. So what will happen here is, since your vertex set was V, you partitioned into the P set and the Q set. So every vertex of P will be connected to every other vertex of Q. Suppose I have a vertex A in the P set and B, C, D, E vertex in the Q set. So every vertex of P is connected to every other vertex of Q. That's all. Like this. Similarly, if I have, let me take S. Then S is connected to B, C, D, E, like this. So this kind of condition is there for the complete bipartite. So bipartite is there plus this special criteria like this. Every vertex in P is adjacent to vertex in Q, which means connected to every vertex in Q. Understood? And obviously no edges from P to P and Q to Q, otherwise it won't be independent sets. Now symbol is what? For the complete graph we had symbol Kn. Now for the complete bipartite graph, the symbol is Kmn. Please make a note, very very important. This is complete graph, this is complete bipartite graph. So what is this M, N? You know it, it's vertex number, but M is the vertex number in the P set, N is the vertex number in the Q set. That's the only difference. Understood? So the symbol remains same. You can say for complete, always remember complete, okay sir, okay K, complete graph K. For normal, Kn. For bipartite complete, M, N. Why M, N? Partitioned, bipartite, two partitions. M vertices in the P set, N vertices in the Q set. Easy. So let me take one example, K2, 3. So P set will have 2 vertex, Q set will have 3 vertex, such that every vertex is connected to every other vertex like this. So if you see one observation, you will find very interesting that total vertex here is what? Obviously addition, 2 plus 3. Okay. Number of edges is what? From this we are getting 3. From this we are getting 3. Right? So it's like 3 outside and 2. And if you see in general calculation now, you will find the number of vertices are M plus N. See, 2 plus 3, M plus N. And the number of edges are like M into N. Okay, check M into N. Number of edges, M into N. So this is what the important thing you have to keep in mind. Whereas when you had the complete graph in general, number of vertex is N and number of edges was NC2, so N into N minus 1 by 2. But number of edges here is M into N. Understood? So difference should be very much clear. In the GATE exam, anything can be asked. So this was all about your bipartite graph, and then we have one last question, or you can say a proof, a theorem. For bipartite graph, not just complete bipartite graph, in general for a bipartite graph with n vertices, maximum number of edges is n square by 4, or you may say, okay, I will prove it by this thing, okay, by the example. But In books it is given like this, okay, but you can extend it by saying n is even or odd, this thing will work. Okay, this works good when n is even, this thing works perfect when n is even or odd. Okay, nevertheless, why this thing is happening, sir? For bipartite graph, if we have n vertices, maximum number of edges, I do not know what just I did right now. I just wanted to say maximum number of edges, right? So maximum number, remember this thing, not compulsory, but the most number of edges would be n square by 4, and most number of edges is present in which graph? In which graph? Complete bipartite graph. Okay, most number of edges is there in the complete bipartite graph, but we can get the bipartite graph which is not a complete but still a bipartite, right? Okay, now the question is, prove it. We can prove it. Suppose I have a graph, it has vertex set V. I can split into two sets, V1 comma V2. If I add the vertices, the count is coming n vertex. That's what they are saying for bipartite graph with n vertices, which means if I have vertex set V, the counting is n. I'm just doing the partition, so V1 and V2. So V1 plus V2 set, like P set plus Q set, addition will be n only, n number of vertices. Suppose this V1 is x. The count in the V1, how many vertex V1 has? X vertices. Then what would be the count for the V2? N minus x. Just rearrange. If V1 is x, V2 would be n minus x. Okay. So V1 is having x vertices, V2 is having n minus x vertices. Now you need the number of edges. Number of edges in the partition. It is what? M into n. So m into n means multiply this two. This is kind of m, this is kind of n. That's what m into n meant, that both of them you should multiply and then you will get the number of edges. So V1 into V2, which is nothing but x into n minus x. Now it's like you needed the maximum number of edges. So maximum number of edges, it's like the maxima minima question. Mathematics, calculus, maxima minima, one variable. That kind of concept. So mod E max is what? Mod E max is like, if this is treated as function of x, x multiplied inside, so nx minus x square, differentiate one time, so n minus 2x equated to 0 to get the stationary point. So x is equal to n by 2. Check the stationary point minima or maxima. For that, double derivative test, single derivative is there, one more time derivative with respect to x, so minus 2. Replace x with n by 2. If you replace x with n by 2, you are getting minus 2. Negation. Negation means you are at maximum. If you are at maximum, done. This point is the point of maxima. So you needed the maximum value of the function, isn't it? You are in search of mod E max. Mod E max means maximum value of this function. At this point you are getting the maximum, so substitute that point. X is n by 2 there. So x is n by 2 is the maximum point, substituted here, and you are getting n by 2 into n by 2, which is n square by 4. Okay, so number of edges maximum is n square by 4, which is very obvious. Suppose you have number of vertices 4. Now you can split like 1 3 or 2 2. Don't say 3 1 because same combination, 1 3 3 1, same thing. So if you need number of edges, it is m into m. So this is m, this is n. The multiply, you will get 3 here, multiply, you will get 4 here. So you got maximum where? When you did equal splitting. So when you do equal splitting and then you do the multiplication, you will get the maximum number of edges. This is what the basic concept is. The problem is, if I have odd, then what will happen? 1 4 2 3, that's it. Other than that, we'll have 3 2 again, which is nothing but repetition, 4 1, which is repetition. Don't say 5 0 because 0 is not allowed. There should be at least one vertex. So mn, like this. Multiply, you are getting 4, multiply, you are getting 6. So that is the maximum. If you try here 5 square by 4, are you getting 625 by 4? No, you are not getting 6. What you are getting is 6 4s are 6 point something something. You may say it as 6, but how to round off then? So for that, whenever you have odd, you can use this logic. What logic? Whenever n is odd, you may use this logic to avoid the confusion. The logic is floor function of n by 2 multiplied with the ceiling function of n by 2. Now check. N was 5, 5 by 2 floor function, 5 by 2 ceiling function. So what is 5 by 2? 2.5, right? Why I need the calculator? Just for the students who are from diploma, C 2.5. Okay, nevertheless, I should not make like this jokes, otherwise they will trigger. So floor function of 2.5, ceiling function of 2.5. What is floor function of 2.5? Floor means the lowest integer. If 2.5 is here, in the left hand side, whoever is the highest integer, you have to select that, which is 2. So you have to select 2. 2.5, whenever I say ceiling function, top. So look at the top. Among that, who is the lowest integer? Select that, 3. Okay. So I hope you understood. 2 into 3 6, that is the answer. We have proved by the branch style as well why 6 was the answer, but this thing works very beautifully if you try. That's it for today. I hope everything is crystal clear. Let me give a quick recap what we have studied in today's class. Independent sets like this. Then while understanding the definition of the bipartite, we understood P and Q independent. Then we have seen the process on how to find the bipartite. The trick was given, but the super trick was like this. Cyclic graph, if length is even, bipartite. Odd, not a bipartite. If triangle shape is present, not a bipartite, but triangle should have all the vertex at the corner, not like this. Okay, so be very, very cautious. That's a trap. And then we have seen some key notes like edges may or may not be present. Still we can say bipartite. And Kn, which is regular, not regular, complete graph. Okay, do not get confused with the regular and the complete. When I say K, then it is K regular, but when I say Kn, that is a complete graph. So complete graph is bipartite only for K2, and then a complete bipartite graph is like Km, and the uniqueness was every vertex from P is mapped to every other vertex in the Q. That's how you have seen. Therefore, the number of vertex here is m plus n, and the number of edges are m into n. If somebody asks you in bipartite graph the maximum number of edges, then it is in the equality when m and n both are equal, n by 2, n by 2. Okay, so that is n square by 4 if the summation is n vertices split n by 2, n by 2. Equal, you will get the maximum number of edges. Understood? That's it. We have seen the proof as well. Thanks for watching the lecture. In today's class, we are going to solve gate PYQs on 𝐏𝐻𝐿-ħakimi theorem and different types of graphs. So let us start the lecture with the very first question. Pause the video, try, then look at my solution. Tried? The question says, which one of the following is true for any simple connected undirected graph with more than 2 vertices? We have 4 options. Now, whenever this kind of question comes, students get stressed, they get tension. No need to worry. Why? Because in discrete mathematics, majority of the time, our trick remains same. What is the trick? The trick is take one example, then analyze the options, eliminate the wrong options. Eventually, you will land up at the right option. As simple as that. So same thing I'm going to do for this question, and then I will give you one important note. Okay, so let us see the technique. The technique is the given data is saying simple connected undirected graph. Okay, with more than 2 vertices, which means vertex cannot be 2. It should be more than 2. It can be 3, 4, 5, so on and so forth. So among them, which of the following is correct? I will make one graph of 3 vertex, cycle graph. So they are talking about what? They are talking about the degrees. So I can see here degree 2, degree 2, degree 2. So no 2 vertices have the same degree. 2 vertices are having the same degree. Why you are saying no 2 vertices are having the same degree? Wrong. Option A is wrong. At least 2 vertex have same degree. Yes. At least 3 vertices have the same degree. Yes. All vertices have same degree. Yes. Take one more example. What if I take this example? Degree 3, degree 2, degree 3, degree 2. At least 2 vertices have same degree. At least 2 vertices have same degree. Makes sense. At least 3 vertices have same degree. No, we cannot find 3 vertices having the same degree here. All vertices have the same degree. Absolutely not. So option elimination says option B is correct, and that statement is nothing but the corollary of the 𝐏𝐿-ħakimi theorem. What is the corollary? That if you have simple connected undirected graph with more than 2 vertices, then always you will get at least 2 vertices having the same degree. Okay, so note it out. Now going to the next question, pause the video, think, then look at my solution. Try. Okay, if you have tried, then it's my turn. First of all, they are saying the degree sequence of a simple graph is the sequence of the degree of the nodes in the graph in decreasing order. Okay, we know it very well. We can see here in the option. Nevertheless, which of the following sequences cannot be the degree sequence of any graph? Cannot be the degree sequence, not a degree sequence. So now, not a degree sequence, you know very well. 𝐏𝐻𝐿-𝐃𝐑𝐦 theorem helps us to find whether a simple graph can be made or not, which means degree sequence exists or not. So I can use that. Indirectly, always you have to get the idea. We have to use which theorem in which question. Directly, nothing would be mentioned that use 𝐏𝐿-𝐃𝐑𝐦 theorem and solve, or use handshaking theorem and solve. You have to analyze by yourself. Understood? First step. Now the problem is we have 4 degree sequence and then we have option, and I was like, to check 𝐏𝐿-𝐃𝐑𝐦 for every sequence will be very time taking. So do we have any tricks and techniques? Then absolutely, I got a basic concept which can be used as a trick by observing the degree sequence. See, the degree sequence is saying we have how many vertex here? 3 plus 3 plus 2, 8 vertices. Here also 3 plus 3 plus 2, 8 vertices, right? 3 plus 3 plus 2. Next also 8, next also 8. Basically all the degree sequence are having 8 vertices. If that is the stuff, then I can say the maximum degree for all vertices for all the graph will be what? 8 minus 1, which is 7. If maximum degree is 7, this sequence is okay, this is okay, this is okay, but this is not okay. They are saying the degree is 8. Degree 8 not possible, maximum degree is 7 only. So this degree sequence is wrong, and they need the wrong degree sequence. See, cannot be the degree sequence. So this cannot be the degree sequence. Okay, cannot be the degree sequence. 4 should be there in our option. 4 is not there in the option. Wrong. 4 is present, 4 is present, 4 is present. Okay. So one option is gone. Now I have to just check for the degree sequence 2 and 3. Which among them cannot be our degree sequence? That would be the correct answer. So for that I have to use some technique now. Can I use any other technique? You might be thinking of summation degree should be even. Apparently summation degree is even in both these stuff. Then what to do? See, no need to check for the 1 since it's already eliminated, and no need for the first degree sequence checking since that is not present in our right options. If I say in KBC style, that option is eliminated. Okay, only we have 3 options, B, C, T. Okay, so I got no choice. Use the 𝐏𝐿-𝐃𝐑𝐦 theorem for this degree sequence. Okay, so first I copied, then I use the algorithm. The 6 says remove from here 1 time, 2 time, 3 time, 4 time, 5 times, 6 times, right? Do the subtraction. Now calculation is 5, 5, 5, 2, 2, 1, 2. Now is it in the decreasing style? No, so make it in the decreasing style. Now remove this 5, 1 time, 2 time, 3 time, 4 time, 5 time. Now do the calculation. 4, 4, 1, 1, 1, 1, right? 4, 4, 1, 1, 1, 1. Now is it decreasing? Yes. Remove this 4, 1 time, 2 time, 3 time, 4 time. Do the calculation. 3, 0, 0, 0, 1. Now sort 3, 1, 0, 0, 0. If you do now decrease, then you will get negative degree. Negative degree not possible. So this degree sequence not possible. They need not possible. 2 is not possible. So 2 is not possible in which option? In option D only. Therefore B, C is wrong. Option elimination. No need to check 𝐏𝐿-𝐃𝐑𝐦 theorem for all the degree sequence. This is how smart you can be in the GATE exam. So the correct answer is what? Option D. Understood how to solve this kind of question pretty fast? If yes, then we can move forward for the next question. And do not worry, all the detailed solution is there in the notes folder. Do not be afraid, sir, you have erased some lines, erase some calculation. Do not worry, everything is there in the notes folder. Pause the video and try this question, then look at my solution. Tried. The question says an ordered n tuple like this in the decreasing fashion is called graphic if there exists a simple indirected graph with n vertices having degree. Okay, which of the following 6 tuple is not graphic? So graphic here means I hope you got the idea. not a degree sequence. Okay, I mean not graphic means not a degree sequence, but this kind of thing is nothing but they are saying graphic, which is our degree sequence. They are changing the term of degree sequence to a graphic. So basically what we have to find is not graphic, which is not a degree sequence. So among this, which of the following is not a degree sequence? I have told you in the class, if you have even ones, then they can cancel in the 𝐏𝐿-𝐃𝐑 and it's possible. What about this? This is nothing but our graph like this. Do you remember? Yes, sir, it is hexagon. See, every vertex is having a degree 2 and we have 6 vertices. What about this thing? We do not know. We have to use 𝐏𝐿-𝐃𝐑. So 3, 3, 3, 1, 0, 0. Remove this 3 1 time, 2 time, 3 time. Calculation is 2, 2, 0, 0, 0. Remove this 2 1 time, 2 time. Oh, you will get the negative degree, which is not possible. So this is not possible, not a degree sequence. Yes, C is not a degree sequence. Done. No need to check for the D. Even if you use the 𝐏𝐿-𝐃𝐑 and check for the D, you will get it as a degree sequence. Understood? Now, let us solve GATE PYQs on the graphs. Pause the video, try, then look at my solution. Tried? I do not know, a lot of students will make mistake here. They will say, sir, by looking at the option, our brain was like, yes, n into n minus 1 by 2 we have seen in the class. So that is the answer, right? Wrong. They are asking how many undirected graphs can be constructed out of the given vertex set, this thing of n vertices. How many undirected graph? They are not talking about how many number of vertices, how many number of edges. No, how many number of graphs they are asking. This is what they are asking. So to solve this kind of question, my way is again not going by the generalization. My way is using the example substitution trick to eliminate the option, apparently reach at the answer. I will do that. And if you want, you can use the probability technique to get the answer as well. But what I want to say here is there is a little bit of problem in the question. They have not mentioned about the graph has a self loop or not. See, if you say, sir, what about the multiple edges? If multiple edges are present, then infinite edges I can create, then infinite graphs can be made. So that's not my concern. My concern is about the self loop. They are not mentioning about the self loop. So even if in the exam that kind of scenario you are facing, assume this is the question without self loop, unless they are mentioning. So error in the question, I agree, they should mention about the self loop, but if nothing is mentioned, then you assume it as a simple graph and then you comment on the answer. Okay, so the correct answer is D. The reason is, if I take n is equal to 1 vertex, then number of graph only 1. This is our phi 1, only one graph can be made. So if I substitute n is 1, this is 0, n is 1, this is 2, but answer is 1, answer not 0 and 2. So this is wrong. If I substitute n is 1, 1 factorial 1, what about here 2 to the power 0, 1. So this is making sense. So I substituted n is 2. N is 2 means 2 vertex, 2 kind of graph like this or not connected graph, correct? So 2 graphs can be made. So when I substituted n is 2, so 2 factorial is 2 and this calculation is also giving me 2 only. Isn't it so? Yes. Then I failed again how to eliminate the other thing. So we have to move forward. N is equal to 3. So if you substitute n is equal to 3, then what you will get? N is equal to 3, no one is connected, phi 3, one of the graph. Now one edge graph you can make, connect this two and leave. So one edge graph, or you can connect this two. So again one edge graph, or you can connect the first and the last vertex, one edge graph. So one edge graph, 3 you can see. See carefully, this was 0 edge. Here edge is 0. These are the example where edge is 1. These are the example where edge is 2. Again that combination I have used, that first, second, third is connected, or first, second, first, third connected, second, third, first, third connected. So 2 edges, 3 graphs you can make, and edge 3 only 1 graph you can make. So total counting if you do is 1, 3, 3, 1, which is 8. So which of the following will give me 8 when n is equal to 3? 3 factorial is not 8. So C is wrong. Apparently A, B, C wrong. Only option D is right. Understood? So option elimination, substitution technique is the best thing you can do in the discrete maths to get answer pretty fast. To the next question. Pause the video, try, then look at my solution. Right? The question says maximum number of edges in an n node undirected graph without a self loop is. Now this is very good because they are framing without self loop. So without self loop means we are talking about the simple graph. So in simple graph, you tell me the maximum number of edges. Sir, it occurs in the Kn. Maximum number of edges is n into n minus 1 by 2. Straight away the answer is option B. Very easy. And if the question in future comes with a self loop, then we'll say that our answer is maximum number of edges without self loop plus maximum number of edges if you include the self loop. So every vertex will have a self loop. So n vertices will have n self loop. So n self loops. Right? Now E max is n into n minus 1 by 2 plus n. So do the calculation. N into, okay, let me write in this way, n square minus n plus 2n by 2. So that is equal to n square plus n by 2. So that is n into n plus 1 by 2. So that is option D. So if they ask with self loop, then you will say without self loop plus consider all the self loop. Without self loop is n into n minus 1 by 2, and if you consider the self loops, n vertices will have n self loop. So add them, the answer comes out to be n plus 1 into n by 2. That is one more good question if in future GATE exam they ask. Try the question number 3. Maximum number of edges in an acyclic undirected graph with n vertices is what? Pause the video, think. Now you are very familiar with my technique. Sir, you will use the substitution technique. Obviously. So acyclic. So if I take n is equal to 3, I will get a cyclic. So when vertex is 3, number of edges is 3. Right? That's obviously the minimum and the maximum. You can say that it's 3. But if it is not cyclic, then it should stop here. Right? We should eliminate this edge. Then the maximum edge is 2. So n is 3, maximum edge is n minus 1. Makes sense? When n is 3, the maximum number of edges for the acyclic, this example is acyclic since cycle is not made. This is cyclic since cycle is made. So when n is 3, I got here 3 minus 1, here 3, 3 plus 1, 6 minus 1. Right? Our answer is 2. Answer is 2 only present in option A, not in the other options, so other options are wrong. Easy, understood? Very simple substitution technique. Try the next question. Pause the video, try, then look at my solution. The maximum number of edges in an bipartite graph on 12 vertices is, you know the derivation I have explained, the maximum number of edges in the bipartite, it was n square by 4, and luckily here n is 12, otherwise you can use that floor function of n by 2 into ceiling function of n by 2. That will also give you the correct answer if n was odd. But nevertheless, here what is the answer? The answer is 12 square by 4. Put that into the calculator. You will get 36 as the answer. Straight away, we have seen the derivation and proof in the class. So no need to repeat again. I know you know the concepts and the derivation. Try the next question. Let T be a tree with 10 vertices. The sum of the degree of all the vertices in T is. Pause the video, think. Tried? So when I say tree means like this, chain reaction, chain. So if I have 1, 2, 3, 4. If I have 4 vertices, the number of edges is 3. So if I have n vertices, then the number of edges is n minus 1. Already we have seen this kind of questions earlier. So now they are saying we have a tree with 10 vertices, n is equal to 10. The sum of the degree is what? Sum of the degree is twice the number of edges, handshaking theorem. Oh, so this was a handshaking theorem question. Okay, but based on the tree graph. So here see carefully, E is what? E is n minus 1, n is 10. So 2 into 9, 18 is the answer. Yes, 18 is the answer. Try the next question. Consider a simple undirected graph of 10 vertices. If the graph is disconnected, then the maximum number of edges it can have is. Oh, so this was something new. That if the graph is disconnected, then the maximum number of edges what? Because if this thing was not there, then we know for sure that the maximum number of edges n into n minus 1 by 2. Now they are giving a condition. The condition is if the graph is disconnected, then the maximum number of edges what? So basically among that 10 vertex, one vertex you make isolated. Okay, so one vertex you make isolated and then you check what is the answer. So if you try if you try, then you may simply say, oh, then we have 9 vertices, and then we can say K9 answer, like n into n minus 1 by 2 is the maximum number of edges, which is 9 into 9 minus 1 by 2, which is 9 into 8 by 2. 2 1s are 2 4s are, the answer is 36. This is one way to solve. The other way to solve is, you will say, in general we know that if this condition was not there, then we know that the maximum number of edges is n into n minus 1 by 2. Right now they are saying that if the graph is disconnected, so there would be among this vertex, there would be one vertex which I should remove. I should erase those edges from that isolated vertices, right? If you consider that all the vertex are connected to each other, the 10 vertices are connected to each other, this is what the thing is. But here among that 10, one is isolated, okay, and you mistakenly consider those edges also from the isolated vertices in this calculation. So I am erasing that, subtracting that edges from the isolated. Suppose I am that isolated, I will be connected to the 9 vertices, so 9 edges, right? 9 edges I have to remove. Now you do the calculation, you substitute n is 10, you will get the same answer. So 5 into 9 minus 9, 9 outside, 5 minus 1, so 9 into 4, again 36. So anyway you can solve, it's up to you, you will get the same answer. Agreed? So there was one more way to solve this question. The method 2 was simply say that 1 is isolated and 9 vertices are joined. So simply 9 into 9 minus 1 by 2 is the answer. Easy. That's it. So we are done for today. Thanks for watching the lecture. In today's lecture, we are going to study about coloring. Now your question might be, sir, what to color? We are going to color vertex with some condition. You cannot color as you want. There are some condition. And then we have further topics connected to it. So a lot of things to study. Let us start the lecture with the very first topic, which is vertex coloring. Now, to understand this, I will take one simple example, then we'll read the definition. Suppose I have a graph like this. 4 vertex connected by this edges. Okay. Now, to color the vertex, we have 4 vertex. So you can say I am going to color all the 4 vertex by different colors. You can take red, green, blue, yellow, any color you want. So this is one way to color. What is the first condition? Take every vertex color different and you can write. But then if you want to minimize the color, you don't want to use 4 types of color, you want 3 types of color, 2 types of color, 1 type of color, then what to do? Is it possible? So for that, the condition is vertex coloring says you can assign the colors to each vertex such that no 2 adjacent vertices share the same color. That you have to keep in mind. So if the first vertex is red, then the adjacent vertex cannot be red, this cannot be red. Can this be red? Yes. Similarly, if this vertex is, let us say, yellow, then adjacent vertex cannot be yellow. Then you can use any other color, let us say blue. So this is also a valid way of coloring where you have used 3 colors to color the vertex. Okay. And the name for this kind of graph is known as proper coloring of G, or simple vertex coloring, because we are dealing with what? We are dealing with simple graph. There are no self loops, there are no multiple edges. So you can say as simple vertex coloring, because at the end of the day, we are coloring only the vertex. The third point is, if G has n coloring, then G is said to be n colorable. Okay, like here we have used 3 colors, so this is 3 colorable. Previous example was we have used the 4 colors, right? So 4 colorable, all the colors are different. If you have understood this thing, now you can understand the basic idea that if I have this graph, this can be colored in many ways. One way is you can use all the different colors and you can say we have 6 vertices, 1, 2, 3, 4, 5, 6. So 6 colorable graph. You can take any 6 color you want. If you want to minimize, then you can do the minimize and you can make minimum 2 color and you can do the vertex coloring. Like if this is red, adjacents cannot be red. This can be red. Again, adjacents cannot be red. So this can be red. You can see adjacents are not red. Now the vacant space can be filled with the next color. Let me take blue. So if this is blue, adjacent cannot be blue. If this is blue, adjacents cannot be blue. If this is blue, adjacents cannot be blue. So we have used only two colors and we have filled this vertex coloring. So I hope you are getting the idea. The definition says the vertex coloring should be such that no two adjacent vertex have the same color. Okay. You can also use 3 colors to fill the graph. You can also use 4 colors to fill the graph as per your requirements. As you can see that if this is blue, adjacents are not blue, but I'm making sure that I want 3 colors. So I'm taking blue here and not blue here. Why? If I take blue here, then again 3 vacancies where I can place red and I can say 2 color graph, but I need 3 color graph. So what I'm doing is blue, blue, red, red, green, green. So in this way, the definition is also satisfied. Adjacent vertices are not having same color, and we have used the 3 color for this graph. Then you can see 4 color graph you can create. The basic idea of vertex coloring, is it clear? The definition, the condition, everything. Now, in real life, we always try to minimize the thing. We have to be frugal. Think this color as money. So you won't spend unnecessary money. You will only spend money for the necessary thing. So when you are going to use the minimum number of colors for the vertex coloring, then we say it as that number is chromatic number. So what is a chromatic number? Chromatic number is a frugal number, is the minimum number of colors to be used to color the vertices of the graph with the conditions. What was the condition? No two adjacent vertex have the same color. Okay. So if in that way you have filled the graph, then the count of the color is your minimum number of colors, that is chromatic number. Okay, what is the notation of the chromatic number? This symbol. This is not X, this is chi. This symbol is chi. Okay, so we are going to use the chi symbol. So chi of the graph. So whenever you see chi of the graph, what is it? Chi of the graph is the minimum number of colors is used for the vertex coloring. That is nothing but chromatic number. Okay, registered, clear. Now try this question. Tell me the chi number of this graph and chi number of this graph. Pause the video thing, then look at my solution. Tried? Okay. So if you start with coloring red here, adjacents cannot be red. So we'll take new color blue. Adjacents cannot be red and blue. Okay, so we'll take one more color green. So the chi number for this graph is 3. Minimum 3 colors we have to use to draw this graph. What about this? Minimum 3, 4, how many? So if I see red here, adjacents cannot be red. So this can be red, but then adjacents cannot be red. What about blue? Yes, 2 colors are enough. 2 colors are enough. So the chi number is 2. Always think in the minimum way possible, because some student might say, sir, blue and green, then we have 3. Sir, why not here pink? Then we have 4. Yes, there are different ways to color the graph, but we need the minimum colors to be used to fill the graph, to do the vertex coloring. So for that, we are going to use this combination, and the chi number is coming out as 2. Easy, understood, no problem in this. What is a chromatic number? The minimum number to do the vertex coloring. Okay. Now, we are going to find chromatic number for all the special types of graphs which we have studied. You have seen the null graph, the regular graph, complete graph, so on and so forth. So for all the graphs, we are going to find the chromatic number. Tell me if I have phi 1. So null graph with vertex 1, the chromatic number for that is? Chromatic number, sir, there are no edges in the null graph. If there are no edges in the null graph, then adjacent vertices should have the different color. That concept won't come here, and that concept won't come here. Then you can happily say, yes, the color to be used to draw this graph is 1 only. Here also 1 only. Here also 1 only, because edges are not there. Therefore, that special condition is not there, and therefore 1 color is enough to draw the graph. See, red, 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 red. 1 color is enough. So always your chi number is 1 for whom? For the null graph. Easy, understood? Very simple. Now, you have to keep a very important note in your head that whenever you see they are saying we have a graph whose chi number is 1, it's possible only for the null graph. Similarly, for the null graph, we have chi number 1. It's a two-way theorem. Null graph is there, chi number 1. Chi number 1, null graph. Definitely. Okay. Why so? Because this is the graph where you have no edges. Other graph have at least one edge. And since they have one edge means two vertex, this two vertex, so two different color, because adjacent vertices are there, they should not have the same colors. And for that reason, apart from the null graph, every other graph will have the chi number greater than 1, which is minimum they will have 2 and maximum depends on the number of vertices. If we have n vertices, you can use n different colors, right? So, but minimum it should be 2. Understood? Going to the next graph. We have regular graph. So pause the video, try to fill the chi graph, then look at my solution. Okay. Let us see the solution now. So we have a regular graph. What is a regular graph? When all the vertices have the same degree. So when I say 0 regular graph, which means the degree is 0. See, degree 0, this graph degree 0, all the vertex are having degree 0. So all this graph is nothing but what? Sir, they are null graph. For the null graph, chi number is always 1. One regular. You can see one regular graphs. See, degree 1, all the vertex are having the degree 1. So for them, what is the chi number? Is it different for every graph or is it same for every graph? For this, red, green, done. So 2 color I needed, chi is 2. Here red, green can be made since no edge in between. So no special condition for them. So we can again use 2 colors to fill the graph. So chi number is 2. Remember, only these 2 are the special stuff. Otherwise, there is no speciality. There is no direct formula or conclusion for the regular graph. You can check it out here. When you have 2 regular graph, 2 regular means this graph is having all the vertex degree 2. Here also all the vertex is having degree 2. What happens in the coloring? Red, green, blue, chi number is 3. Here red, blue, already dealt with this kind of curves. So here you can see chi number is 2. So we do not have any specific chi number. Similarly for the 3 regular, we do not have some specific chi number. Depends on the graph, we'll figure it out the chi number. Understood? But for the 0 regular and 1 regular, it's always fixed. For 0 regular, it's based on the null graph, so chi number is always 1. For 1 regular, the chi number is always 2 because 1 edge. 1 regular means 1 edge. 1 edge means definitely 2 different colors, so 2 chi number. Okay? Makes sense? To the next graph, complete graph. So you can see complete graph notation was Kn, where n is number of vertices. So 1 vertex this thing, 2 vertex this thing, 3 vertex this thing, 4 vertex this thing. And the condition was in the complete graph, all the vertices are connected to all the other vertices. So you can see this is what our curve looks like. Find the chi number for every curve. I should not explain what are this kind of graphs since we have already studied in depth in the previous lecture. Still my heart says repeat it so that they get revision. For that reason I always speak. Nevertheless, I hope you have tried. What is the answer for this graph? 1 color is enough. So chi number is 1. For here 2 colors are needed. For here 3 colors are needed. For this red, adjacents, everyone is adjacent. This is also adjacent. See, everyone is adjacent. So different color, green. Okay, everyone is adjacent. So green cannot be used. Different color, blue. Everyone is adjacent. So different color, pink. So 4. Can you see? K1 1, K2 2, K3 3, K4 4. What is happening? Sir, the conclusion is for the complete graph Kn, the chi number comes out to be n. Yes. Why so? Because every vertex is joined to every other vertex. So every vertex is having the adjacent vertex, and therefore every vertex color should be different. Therefore n vertex, n colors, chi number is n. That is your minimum. So you can make a note. We got the range of the chi number now. Chi number range. Minimum chi number is 1 for whom? only for the null graphs, right? And then maximum the chi number is n for whom? Only for the complete graph. Okay, so this is the range of the chi number from 1 to n. In between we can have variations, as you can see for the different graphs there are different chi numbers, but minimum and the maximum we got the idea. Minimum for the null, maximum for the complete graph. Going to the next graph, we have cycle graph. Pause the video and try what are the chi numbers for all this graph. Tried. When I say C3, cycle in a 3 vertex and a cycle, so obviously 3 colors, chi number is 3. What about this? Red, red, green, green, chi number 2. What about this? Red, green, red, green, red. Okay, so I guess no sir, here red, red, so problem, we have to take one more color. Okay, now it is okay, so 3. What about this? Red, green, red, green, red, green. Is it okay? Satisfying the definition? Yes. So 2 numbers are enough. Can you see a pattern? Odd 3, even 2, odd 3, even 2. Oh sir, I got the idea. For the cycle graph, when n is odd, the chi number is odd value, that is 3. When n is even, the chi number is also even, and the answer is 2 always. So is it always? Yes, it is always. It is always. Now you can also interpret in this way. Whenever we have cycle of even, they are definitely what? Bipartite. And if something is bipartite, which means we'll have 2 sets, vertex here's, and they are joined in between, right? Like this. Bipartite says this is what your diagram looks like. So the vertices in the set P can take one color. Let me take red. And vertices in the set Q can take one color. Let me take blue. And see, no one is adjacent to each other. So reds here, blues here, edges in between. So every edge will have different colors at the end. And therefore always in a bipartite we'll get the chi number 2. We'll see in the further slide, because there is a catch as well. What is that catch will be explained. But for now you are getting the idea that for the cycle graph, since it was bipartite, the chi number is 2, and when the cycle is odd, it's not a bipartite, so chi number is 3. You can also interpret about the bipartite nature using the coloring. Okay. Now to the 7th concept, which is chromatic number for the wheel graph. So we have 2 wheel graph. Pause the video and try. You know, wheel graph is nothing but connection to the cycle graph. Cycle graph n-1 plus vertex at the center. So I hope you have tried. The problem is the center is connected to every other vertex, so that should be different always. Center is connected to every other vertex, so that should be unique color always. Other thing you can think of, if this is red, adjacents cannot be red. If this is green, adjacent cannot be green. And center should be unique color. Let me take pink, so chi number is 4. If this is red, adjacent cannot be red. But this thing can be red. Yes. Adjacent, now it can be blue. And then center can be a unique color pink. So can I say I used 1, 2, 3. 3 colors. Is it good enough? If it is good enough, then I can say I have made a conclusion from this diagram that chi number for the wheel graph Wn is equal to chi number for the cycle graph n-1 plus 1 unique color for the center vertex, and that's how your answer was coming. Check it out. When n was 4, so cycle of 4 minus 1, cycle of 3. 3 means odd. Odd means chi number 3. So chi number 3 plus 1 color for the vertex, total answer should be 4. When n is 5, then n is 5, cycle of 5 minus 1, cycle of 4 is even, chi number 2, okay, so chi number 2 plus 1 unique color for the center, total answer is 3. Similarly, you can find for the any wheel graph, no need to make the diagram and conclude, okay. Also, if you observe carefully, chi number of the wheel graph is always greater than 2. It is not equal to 2. You won't get the chi number for Cn minus 1 here as 1. Okay, you can see chi numbers are what for the Cn, it is 2 or 3. It cannot be 1. Since this is not 1, so 1 plus 1, 2 is not possible. Since 2 is not possible, bipartite is not possible, which means wheel graph cannot be bipartite. Because for the bipartite graph, we have seen the chi number was 2. Okay, so Wn is not bipartite since chi number is always greater than 2. It is not equal to 2. Makes sense? Easy. So graph and coloring, very easy concept, just basics. If you have the good idea of the graph and basic analysis, you can comment on any kind of graph and n number of questions can be created by interlinking the concepts. So I'm giving you all the stuffs and varieties how to think. Okay, going to the next graph, which is n cube graph. You can see we have this n cube graph. Tell me the chi numbers for that. Pause the video, think, then look at my solution. Tried. So for the first one, red is enough. 1 here, red, green, 2 here, red, red, green, green, 2 here, red. Adjacents cannot be red, so let me take adjacent green, green, green. Okay, this thing can be red, yes, but then adjacent cannot be red, so green. Any other adjacent? No. This thing, if I take red, adjacent cannot be red. Makes sense? This thing, if red, adjacent cannot be red. Oh, so 2 chi number is enough. So can you see in the n cube graph only the n equal to 0, n equal to 0 has the chi number 1. All the others, when n is not equal to 0, have chi number 2 always. Okay, so this is the observation which we have seen. Understood? So that's what I have written here. And since they are 2, therefore Qn is always bipartite graph when your n is not equal to 0. For n is equal to 0, it is not bipartite, because for bipartite you will partition into the 2 set and this set should be non-empty. But since you have only one vertex here, the other will be empty, and if it is empty, then it is not a bipartite. Therefore I am saying that for n equal to 0, this will never be bipartite, but for Qn when n is not equal to 0, always a bipartite. Make sense? Okay, now we have bipartite graph. So in bipartite graph, see, you have 2 chromatic number, you have 2 chi number. How come, sir? See, one is phi n when n is greater than 1, and all the other graph. Okay, apart from this, all the other graph when it is not phi n. Okay, now I will take one example. Problem just arrived for this, the null graph version. Otherwise, all the bipartite which is not a null graph is always having the chi number 2. Okay, so always remember that when bipartite thing is there, we have 2 chi number. One is that special condition for the null graph. Always you will have the bipartite graph for the null as chi number 1, and for the other graph which is not a null graph, the bipartite graph is present and the chi number would be 2. Okay, so here you can see that I have drawn phi 2. Is it a bipartite? Definitely it's a bipartite. Why? Because this is first set, this is second set, this is P, this is Q. They are satisfying the definitions. P and Q are independent set, union is the vertex set, intersection is the null set. Okay, they are satisfying the definition. So this example is a bipartite. Now, if I talk about the coloring, red, red. So chi number 1 is enough. Okay, so minimum number of color 1 is enough. Chromatic number is 1, chi is 1. So chi is 1. So chi can be 1 in the bipartite when you have null graphs. All the null graphs are the bipartite? No. All the null graphs are not the bipartite, because if you take a phi 1, this is not a bipartite. Okay. Apart from phi 1, all the graphs are bipartite. Therefore, I have written when n is greater than 1. All the null graphs are bipartite, and for them only chi number is 1. Otherwise, the graphs which are not the null graph, always they will have the chi number 2, as this example already discussed multiple times. Chi number 2. Easy now, crystal clear. Therefore, I told you in bipartite 2 possibilities were there in the previous slides. Now, coming to the complete bipartite. For complete bipartite, always the chi number is 2. See, complete bipartite, the notation was K, M, N, right? And you make any graph. Either both of them are same, M equal, N equal 1. So red, green, chi number 2. or you may take m is equal to 1, n is equal to 2. So m is 1, n is 2. Every vertex is joined to every other vertex in this way such that they are following the bipartite definition, right? So this is our complete bipartite. And if that is the thing, again this is red, adjacent should be different. So again 2 colors are enough to draw the graph. You take any example you want, okay? Always what you will find is, you will find this is our P set, this is our Q set, this is our P set, this is our Q set. So P set will require 1 color, Q set will require 1 color, total is 1 plus 1, 2 color is enough to draw the graph. Therefore, complete bipartite graph will always have the chi number 2. Now you might be thinking, then sir, why bipartite graph had the chi number 1 or 2? Because of that null. Because of that null. What happens here is, in complete bipartite, you cannot take phi 1. Phi 1 is invalid. You cannot take that. Even you cannot take phi 2. That is also invalid. Sir, why I cannot take phi 2? Because if you take phi 2, what will happen is, here one vertex, here one vertex, right? But the definition for the complete bipartite graph is every vertex is joined to every other vertex from P to Q. So phi 2 will not join this. If phi 2 will not join this, this won't be the complete bipartite graph. And if this is not the bipartite graph, we cannot apply the concepts of the complete bipartite graph here. So I hope this makes sense, that the null graph won't come in the complete bipartite graph because of not matching the definition. The definition says what? Every vertex from P will join the every other vertex of the Q. But in the null graph, nobody joins nobody. And that was the reason. So this line, this side won't come, only this side will come in the complete bipartite graph, and therefore the chi number is 2 always. Make sense? Easy. Now we have some special note and the lecture is done. The first note is, if the chi number is k, then you will find degree for all the vertex in the graph is greater than equal to k minus 1. Yes, you can verify. You can take any graph. What is the chi number here? 2. Okay, so degree of any vertex in the graph should be greater than equal to 2 minus 1, which is minimum the degree of the vertex should be 1. You can check here, degree 2, 2, 2, 2. So everyone is having degree which is greater than equal to 1. You can check here also. You can obviously, so everyone is having here 3 degrees, right? So it is greater than equal to 1. You can check any problem you want. You can check here also. What I just told you, if chi number is 3, then all the vertex will have the degree which is greater than equal to 3 minus 1. So everyone is having degree greater than equal to 2. So here if I check, it's 3, here it's 4, here it's 3, 3, 3. So yes, it's greater than equal to 2. You can try for all the other because this always works. This is true. Now coming to the next statement. Every tree with number of vertices 2 or more will have chi number 2 always. And if chi number is 2, can we say every tree with number of vertices 2 or more exists? Or it's definitely this graph only? If this is the thing, then this graph only. Can I say? Pause the video, think, then look at my solution. It's a two-way theorem or one-way theorem? The answer is, it's just a one-way theorem. If you have tree with number of vertices 2 or more, then you will see chi number is 2 always. But if chi number is 2, then may or may not be a tree graph. Sir, any example? I have example. See, this is a tree graph. This is a tree graph. You try to color the vertex. If this is red, this should be blue. This is red, this should be blue. This should be red, this should be blue, right? So you can see no condition is harmed. The condition of the vertex coloring is satisfied. All the vertices are colored in such a way, no two adjacent vertex have the same color, right? So only 2 colors are needed to draw the graph. So minimum number of color is 2, which means chi number is 2. So for every tree with number of vertices greater than equal to 2, minimum it should be 2. If you have a tree with one vertex, only one color, okay, then this failed. Therefore I told you number of vertex should be minimum 2 or more. If it is 2, if it is more, it should be in the tree form, tree, like this, tree. If it is in the tree form, then red, blue, red, blue, red, blue, red. You can see 2 colors are enough. So chi number is 2. So if it is a tree with number of vertices greater than equal to 2, then chi number is 2, but the other way around may or may not be true. Check it out. See, this thing is saying that chi2 we got a tree, but this is saying chi2 but we are not having a tree, we have a closed curve. Check. This is cycle of what? Cycle of can I say 4? This is cycle of 4. Yes, because number of vertex is 4. Makes sense. Easy. If easy, here you got chi number 2, but it was not a tree. So this thing is satisfied. That one way theorem like this, other way theorem is may or may not be true. Every graph I explained in depth so that you have no problem, and every analysis is also done so that if gate question comes on those analysis, you are already ready to tackle them. So in start, I thought you would be very much in tension, a lot of things we have to study, but as we move forward in the lecture, you found it was very, very easy. So thank you for watching the lecture. That's it for today. In today's class, we are going to solve gate PYQs on chromatic number. So let us start the lecture with the very first question in front of your screen. Pause the video, try, then look at my solution. Tried? The question says the minimum number of colors required to color the following graph such that no two adjacent vertices are assigned the same color, which means you have to find the chromatic number of which graph? Of this graph. How to do? Either you can use the colors green, blue, yellow, so on and so forth, or you can use the numbers 1, 2, 3. This is very effective to at the end get the answer. So I am going to use number. If I number this node as 1, which is like color of this vertex as 1, then the adjacent vertices cannot be 1. Apart from that, you can color the vertex as 1. If I do this vertex coloring as 1, then the adjacents, this is not adjacent, the adjacents cannot be 1. For this, the adjacents were this thing. So all the nodes now cannot be 1. Only 2 node, or you can say vertex, can be 1. Similarly, fill the next vertex color as, let us say, 2. If this is 2, adjacents cannot be 2, but this can be 2, then adjacents cannot be 2. Okay. If I take this as 3, then this is 3. If I take this as 4, then this is 4. 4 colors minimum it is required, and yes, the answer is C. Understood? You can use the colors like green, blue, pink. You can use that, yellow. I have no issue, but at the end you have to count how many colors you have used. So 1, 2, 3, 4. 4 is the answer. Understood? To the next question. What is the chromatic number of the following graph? Where is the graph? Oops. This is the graph. I know you have seen the solution, but try by yourself again. Tried? Okay, now it's my turn. If I color this vertex as 1, then this is the adjacent, cannot be 1. This is the adjacent, this is the adjacent, they cannot be 1, but then other players can be 1. If this is 1, then adjacents cannot be 1, but this can be 1. Then adjacents cannot be 1. Okay, but then this can be 1, right? So 1 can be filled in this 4. Isn't it so? Apart from that, can you make this as 1? No, because this would be adjacent to this vertex. Then I have color 2, 2, 2, 2, and then color 3. Minimum 3 colors are required, okay, to fill this graph. So answer is option B. To the next question. What is the chromatic number of an n vertex simple connected graph which do not contain any odd length cycle? Assume n is greater than equal to 2. Pause the video, try, then look at my solution. Tried? Whenever this kind of question comes, you know my technique is substitution. So start with n is equal to 2. Now you will say, sir, we have two kind of graph. One is this null graph and other is this graph, simple graph. But remember, they are saying simple connected graph. If it is connected, then this is not connected. This is not allowed. This is allowed. If this is allowed, 2 colors are needed to fill this graph. So when n is 2, this is 1. We need 2 colors. We need 2 colors, not 3. So 2 options are gone. What if n is equal to 3? What will happen? 3 vertex can be joined like this. 3 vertex can be joined like this. These are the options. So if they are saying, oh, what they are saying, does not contain any odd cycle. Here we will have odd cycle. So if it is odd cycle, not allowed. This is allowed. So 1, 2, 1. Again 2. When n is 3, colors are 2. So this is wrong. Option A is correct. You can check even for the n is 4. N is 4. 2 colors are enough. 1, 2, 1, 2. Right? 2 colors are enough. So yes, the answer is option A is correct if this is the condition, that odd cycles are not allowed. Okay, odd cycle means like this, cyclic. You know it very well. In the conceptual class we have seen all the concepts, right? Now to the next question. Pause the video, try, then look at my solution. Try the chromatic number for the following graph. Some students are like, sir, 1, 2, 3, 4, 5, 6, 6. No, the 6 are the vertex. They need the chromatic number. So chromatic number, now I know a lot of students will say answer is 3 or 4. Okay, the 4 ones are wrong because you are solving like this. This is wrong. Okay, always remember you will get chromatic number when you try to fill the same colors in the alternate version. Like if 1 is here, try to find the alternate, which means alternate means leave the first adjacent vertex and try for the next. So leave this because this is adjacent, try for the next. But this is also adjacent, try for the next, adjacent, try for the next. So this should be 1. Okay, and some students, if you mark this as 1, then we are going to land up in this problem where we are getting 4 color necessity, but necessity is not 4 color. You can use 3 color as well to get the answer. I will show. If I start with 1 here, then the next vertex is this adjacent, cannot be 1, cannot be 1, cannot be 1, and the immediate next is the alternate, right? So this is 1, and if this is 1, this cannot be 1. Understood? Now you go with the next colors. Suppose this is 2, then this is 2, then finally this is 3. So 3 colors are enough. That is the answer. To the next question, pause the video, try. Tried. Very easy question again. They are asking the chromatic number of the graph. Chromatic number is the minimum number color. Okay, we know all these things, right? So what is the chromatic number of the graph? If this is 1, the adjacents cannot be 1, so give them next color. So adjacent vertices, I am giving them the next color. So if this is 2, then the adjacent vertices can be 1. And finally this is 2. Check. No 2 adjacent vertices are having the same color. So the chromatic number is just 2. Done. That's it for today. I hope you enjoyed the video. Welcome to lecture 6. In today's class, we are going to study 2 topics. First topic is diameter of graph and second topic is operation of graph. Let us start the lecture with the very first topic, diameter of graph. Now please make a note, you cannot find this diameter directly because it's a 2-step process. First step, you should learn how to find distances in the graph, and second step is among those distances, whoever is the maximum is our diameter. Okay, so let us understand this technically and easily by an example. Suppose I have this graph. Then how many vertices? 1, 2, 3, 4. 4 vertices are there. So whenever I say distance, distance will have a start and end point. So start point is a vertex, end point is also a vertex. Now sir, we have many possible pairs like this, starting at 1, ending at 2, starting at 1, ending at 4, starting at 1, ending at 3, starting at 2, ending at 3. Lot of things are there. Agreed. So it's a time taking process. You have to write all the possible pairs and find all the possible distance. Okay, so let me write the possible pairs. Start at 1, end at 2, start at 1, end at 3, start at 1, end at 4, start at 2. Do not say end at 1 because both of them are same because it is undirected graph. So start 1, end 2 or start 2, end 1 is one and the same answer, right? Because it is undirected graph. Now if that is not the possible pair which I have to select because it would be a repetition, then we'll take like this 2, 3. Is it new? Is it okay? Makes sense. 2, 4. Yes, it is new. It is okay. What about 3? 3, 1 is done here. 3, 2 is done here. 3, 3 makes no sense because all these topics are related to non-self loop and non-multiple edges, right? So simple graph should be there. So for that 3, 3 should not be a valid pair. Then 3, 4, yes, I can take 3, 4. That's okay. What about 4, 1, 4, 2, 4, 3? 4, 4 is not possible. So all the possible pairs of vertices I have written. Now, the second step is to find the distance. How to find distance from 1 to 2? Some students are like, sir, we can go directly 1 to 2. We can go indirectly 1 to 4, then 4 to 2. Or we can go like this also, 1 to 3, 3 to 4, 4 to 2. So which distance I have to take? Distance is taken such that you have the minimum number of edges. Okay, so minimum number of edges should be there, then only that path is considered as the distance. So 1 to 2, minimum number of edges to reach, only 1, so distance is 1. Understood? Then 1 to 3, minimum number of edges is 1. 1 to 4, again one step process, minimum number of edges is 1. 2 to 3, 2 to 3, there is no direct connect, so we cannot go in one step. 2 to 3, first you go from 2 to 1 and then 1 to 3, so 2 number of edges I need. Isn't it so? You can say that 2 to 1, 1 to 4, 4 to 3 is 3 number of edges, but what we need is the minimum number of edges to reach at the destination. So I will not take this 3, I will rather take the 2 number of edges path. Understood? 2 to 4, 1, so distance is 1. 3 to 4, 1. Okay, so this was our first step in solving the findings of diameter of a graph. The second step is, among all the distance, for all distance, so whoever is having maximum number of edges, that is our diameter. As simple as that. So among all the distances, check who is having the highest number of edges, this thing. So that is the value of diameter of the graph. Understood how to find the diameter of the graph? First step is find the distance. How to find distance? Check the minimum number of edges required to go from start to end. Okay, so find all the distances, and it's a time taking process because we have multiples start and end in this graph. So all the vertex pair you have to take and find the distances. Second step is, among all the distances, who is having the maximum number of edges? This is the player, so that is our diameter. Okay, understood? Now you can easily interpret the definition of diameter of a graph. Definition says about two things. First, distance. Second, diameter. Distance between two vertices is what? Length or number of edges of the shortest path between them. In short, I have told you distance is minimum number of edges. Same thing they are saying. Instead of E, they are saying length, or they are saying number of edges. And instead of minimum, they are saying the shortest path. Understood? If understood, then the diameter is what? Maximum shortest path length among all pair of vertices. In short, you can say maximum of shortest path length among all the vertices is nothing but for all distance in the graph, right? So that value is your diameter value. In short, you can remember like this. Diameter is maximum among all the distances. Easy? If easy, then tell me the maximum distance in this graph. That is your diameter. So find diameter of the graph. I know a lot of students will say, sir, it's very time taking process, because first we have to find all the distances, and to find all the distances we have to find all the pairs of vertices and find the distances, then among that the maximum value is the answer. So do we have any tricks? We definitely have tricks. Always remember, if you are standing at here, then going to the adjacent sides are easy, so you can reach fast, but going to the opposite side is time taking. So the pair which is having the nature of opposite vertices, that's time taking, so you will spend maximum distance there, right? And that will ultimately give you the answer for the diameter. Getting my idea? Always search for the opposite pairs. Like here, adjacent pairs are quick enough to solve. See, 1 to 2, 1 distance, right? 1 to 3, 1 distance. 3 to 4, all adjacent you can see, 1, 1 distance. 3 to 4, 1. 3 to 1, 1. 2 to 4, 1, right? So 1, 1. But if you go in the opposite vertices nature, 1 to 4, you can't go in one step since diagonal is not there. So you will go first 1 to 2 and then 2 to 4. The distance you will take from going 1 to 4, the distance is 2. Similarly, if you try for 2 to 3, the distance you will take is 2, because number of edges is 2. Check 2 to 1 and then 1 to 3. And finally, you can say this is the maximum. Since this is the maximum, the diameter of the graph is 2. Easy. If easy understood, try this next question. But before going to the next question, this is the summary. So everything is there in the notes folder. Do not write anything. Okay. So to save time, maximum length you will get when you are looking for U and V vertices are opposite in nature, sitting at the opposite nature place. Try this question. Pause the video, try, then look at my solution. Tried? The question says we have to find the diameter of this graph, and if you go for all the pairs 1 to 2, then 1 to 3, 1 to 4, it will be a very time taking process to solve. If you want to solve it fast, use my tricks. 1 is sitting here, the opposite is 4, right? Adjacents are quicker to solve, like one step you will reach, so no point. Even alternate adjacents you can see, they are very quick to find, but the ultimate opposite will take very time. So 1 to 4 will be actually time taking. I hope you are getting my feeling. What's my trick here? So 1 to 4, tell me the distance. A lot of students will say 1 to 3. That's wrong, because distance is the fastest path you have to select. Remember, distance is what? Distance is the minimum number of edges. You have to look for the minimum number of edges. This 3 was the maximum. If you go by this route, then minimum number of edges is 2. So D is 2. Now search for 2. To opposite is 5. You can also think in this way. This is can be the opposite. Okay, so also try for that. Tell me, for 2 to 5, I can see the fastest is 2. You can go like this, but this will take time, 3. So 3 is not the distance, 2 is the distance. 2 to 6, 2 to 6 again 2 step, right? Then talking about 3 to opposite, I can see 6, right? So 3 to 6, that is the ultimate opposite. If you find the number of edges, 1, 2, 3, 3 in this way, 1, 2, 3, 3 in this way. If I use some edges, 1, 2, 3, 4. Okay, so the minimum was 3, right? We can't go in 2 step, we can't go in 1 step, minimum is 3. If I check for 3 to 5, obviously it's a 2-step process, so I won't select that vertex. Talking about 4 to 2, 1 step, 5 to 2, 2 step, 6 to 3, 6 to 3 is nothing but 3 to 6, right? So we are already done. I should stop here and I should comment. I got my diameter. Among all this, 3 is the highest. So maximum is the diameter. So diameter of the graph is 3. Makes sense? Easy? Understood my trick? If understood, now let us go to different types of graphs which you have already studied, like null graph, regular graph, complete graph, so on and so forth. And let us try to find the diameter of all such graphs. Okay. First graph we have is a null graph. Can you find diameter of all these examples? Pause the video, try, then look at my solution. Tried? The first example says phi 1. What is phi 1? Only one vertex. If we have only one vertex, then how you will go to another vertex? Sir, there is no other vertex. We have only one vertex. So the distance here is 0, because if you have any other vertex, distance exists. If you do not have other vertex, then distance is 0. Right? So distance 0, and since we have only one distance, the diameter of this graph of phi 1 is this distance value only, which is 0. Understood? For the phi 2, you are standing at vertex 1, you want to go at vertex 2. Since there is no edge, you will say distance 0? No, you will say to reach at vertex 2, I will take a lot of time, right? Since there is no proper distance, I will take a lot of time. Lot of time means infinite time. Infinite times means distance is infinity. Similarly, 2 to 1, distance is infinity. So diameter is the maximum. Maximum we can see infinity. So diameter is infinity. Here also same problem. Distance is infinity since the vertices are disconnected. So vertices are disconnected, diameter of this graph phi 3 is also infinity. Can I in general say now, whenever we have a disconnected graph, then the diameter is infinity, since if you want to go from vertex 1 to vertex 2, you will take a lot of time. Like if I want to go from India to Africa and there is no airline, then how will I go? By walking or by any other way? So it will take a lot of time. A lot of time means infinity, distance is infinity. So that is the thing. And a very critical observation here is, only when n is equal to 1 you have distance 0. For other values the distance is infinity, which means for the diameter also, this thing is applicable for the diameter also, because diameter is distance here, since we have only one distance in the null graph. Therefore diameter is the distance value. So diameter value is 0 when n is 1. When n is not equal to 1, diameter is infinity, or you may say when n is greater than 1, the diameter is infinity. Okay, remember, for the null graph this is the scenario. If understood, try for the next type of graph, which is complete graph. Pause the video, try, then look at my solution. Tried? What does this question says? This question says we are dealing with complete graph. In complete graph, every vertex is connected to every other vertex. When that happens, always you will get one step answer. See, there is exception as well. When you are dealing with K1, we have only one vertex, no other vertex, so distance is 0, only one distance, that is the diameter. So diameter value is what? Diameter value is 0. If I check for K2, every vertex is connected to every other vertex. I want to go from 1 to 2, one step process. So distance 1, only one distance, diameter is 1. But if you check for K3, every vertex is connected to every other vertex. You go from 1 to 2, or 1 to 3, or 2 to 3, or you go from anywhere to anywhere. Always you will reach in one step. Since distance is 1 for every one, the diameter is 1. For K4 also same thing. See, we do not have here vertex. Okay, we do not have here vertex. Vertex are 1, 2, 3, 4. These are the vertex. You choose any two pair. 1 to 2 one step, 1 to 3 one step, 1 to 4 one step, 2 to 4 one step, 2 to 3 one step. You choose any two pairs. You will always get distance 1, and therefore your diameter is 1. So the conclusion is diameter is always 1 when Kn has two possibilities, diameter 1 and diameter 0. So diameter is always 1 when n is not equal to 1, which is n is greater than 1, and diameter is 0 when n is equal to 1. That's it. That is our conclusion. So everything is there in the notes, no need to write, just giving you the analysis by the example. To the next question. So what is a zero regular? What is a regular graph? You know, right? Regular graph means every vertex is having the same degree. So pause the video, try, then look at my solution. Tried? So zero regular means only one dot, or you may say 2 dots or 3 dots, so on and so forth. If we have 0 dot, if we have 1 dot, 0 dot is not possible. You should have at least one vertex. So if we have one vertex means the distance is 0, so diameter is 0. For here we have two vertex, so distance is infinity between them, so diameter is infinity. And for all the other players, apart from that, the diameter is infinity. So in general, can I say zero regular is nothing but the phi n graph. So in phi n graph we had two possibilities, diameter is 0 and diameter is infinity. 0 when we have only one vertex, and when n is not equal to 1, like n is greater than 1, more than two vertex, so distance is infinity. It's like India to Africa. Talking about the one regular, here you can see distance is 1, so diameter is 1, but here we have disconnect, so distance infinity, diameter is infinity. What about two regular? Two regular means everyone is having a degree 2, so disconnect can happen here? No, because it will have what? It will have a degree, or you may say like this. Can I make like this? Not allowed, because in this graph also every vertex is not having the same degree. If it is not having the same degree, it is not a regular graph, so I cannot make like this. So if two regular graph you see like this, every vertex is connected to every other vertex, distance is 1 always, so the diameter is 1. What about here? Everyone is having degree 2, so it's a two regular graph. Talking about the distance, one vertex 2 3 4. Okay, so we have vertices 1 2 3 4, or you may write it as ABCD. A, B, C, D. So A to C, the opposite will take time, and that is 2. So the maximum distance is 2 if you travel in the opposite A to C. A to B is fastest, adjacent, one step, but A to C will be time taking, and that is our diameter. So you can see there is no direct formula. There is no direct formula or conclusion on the regular graph, and this is not Q, this is phi, just a notation problem here. Okay, that's a null graph notation, right? Phi n. Understood? Same thing is there in the notes, so no issue at all. Talking about the next type of graph, which is cycle graph. Tell me the diameters for all the graphs. Pause the video, try, then look at my solution. Here you will say the diameter is 1 because C3 is like K3 only, right? K3 is complete graph, C3 is also same thing. Now talking about C4. C4 here we have seen already, here the diameter is 2. Previous example. C5. C5 opposites will have the maximum distance 1, 2. Okay, so I can only see 2 as the maximum distance, so the diameter is 2. In C6 opposite 1, 2, 3. 3 is the diameter. C7 opposite 1, 2, 3, 1, 2, 3, 4, but I will choose only 3 because the distance should be minimum, and opposite vertices give you the maximum distance in the graph, so that would be the diameter. What is the diameter? From this to this, 3 distance, that is the diameter. What about this graph? From this opposite to this opposite, 1, 2, 3, 4. If I go from right, 1, 2, 3, 4. So 4 is the answer. The diameter is 4. Easy. So by the trick, it's very simple to find the diameter now. As you can see in the graph, is there any pattern going on? Steadily the diameter value is increasing. Makes sense. But can we generalize? Yes, we can generalize. The answer is diameter of the graph is floor function n by 2. You can try. This is floor function n by 2. When n is 3, 3 by 2 floor function, right? If you check, it would be 1 point something, but you will take the lowest integer, which is 1. So that is the answer. 4 by 2 is 2 itself, 5 by 2 is 2.5, but you will take the lowest value of integer, that is 2. Then we have 6 by 2, that is 3. So 7 by 2, 7 by 2 is again 3 point something. So you will take the lowest integer, that would be 3. Then 8 by 2, floor function is proper integer 4 only. So on and so forth. You can find for C9, C100 and so on and so forth. So it's very simple trick to remember that for the cycle graph, we won't solve manually. We'll rather say diameter of the graph is floor function n by 2. Not ceiling function, it's the floor function. Okay. To the next question, diameter for wheel graph. Pause the video, try, then look at my solution. Tried. Now this center is always a problematic. Because of this center, we'll reach very fast to any other vertex. See, if I'm at 1, reaching at 2 is super fast, reaching at 3 super fast, one step. Do we have a vertex here? Definitely. Wheel says you should have a vertex at the center, so therefore it's a W4 because made from 4 vertices. So 1 to 2 1 step, 1 to 3 1 step, and 2 to 3 1 step, 1 to 4 1 step. So I think everyone is talking to each other in 1 step. So distance is 1, so diameter would be 1. What about here? 1 2 3 4 5. If I want to reach from 1 to 3 the opposite vertices, from which we actually get the diameter answer quickly. It's a 2-step process because 5 will always act as the mediator to reach fast. Okay. So it's a 2-step process. Even 2 to 4, it's a 2-step process. 5 will act as the mediator, and if that is the case, then distance is 2. Maximum value distance is 2. Diameter is 2. What about W6? Again, if you want to go from opposite vertices, let me say A to B, like this thing, then middle will act as the mediator because we have a vertex E at the center. So A to E, E to B, again 2. So 2 is the answer. So I hope you got the idea. It can be segregated into 2 style. W4 will always have the diameter 1. Apart from that, all will have the diameter 2. Isn't it so? In the wheel graph, only for the first wheel, which is W4, you will get the diameter 1. For other graphs, diameter will always be 2. Why? Because center will act as the mediator to reach the opposite. It's very quick. But here, straight away, they are talking to each other. Opposite vertices are talking to each other. So 1-step process. Talking about the n cube, pause the video, try, then look at my solution. Tried. So q0, q1, q2, q3, every question you have solved. Here distance is 0 and therefore diameter is 0. Here the distance is 1, diameter is 1. Since whenever you have only one distance, that is the diameter. Here we have multiple distances. Among that you have to choose the maximum, which will happen in the opposites. What about this graph? If I am at here, the opposite would be this thing. How I can reach 1, 2, 3. 3. Do we have faster way? No. 1, 2, 3. 3 is the only way. If I select this and this opposite, again 3. 1, 2, 3. So any opposites you take, you will get 3, and then you will see n0, 0, n1, 1, n2, 2, n3, 3. So qn. Whenever you have qn, the diameter of the graph will always be n. Now please make a note, n here is not number of vertices. This is the only special graph where n is not the number of vertices. Number of vertices is 2 to the power n. When n is 0, then you can see one vertex, because 2 to the power 0 is 1. When n is 1, you can see 2 vertex. When n is 2, you can see 4 vertex, so on and so forth. Easy, understood. So this was a very simple trick for the n cube graph. The answer is qn is n diameter. Now for bipartite, do we have any formula? No, we do not have any formula. Okay, you can try this question in bipartite and tell me the respective diameters. You will say, for this question, sir, these two graphs are disconnected, therefore the diameter is infinity. Wrong. This is not disconnected. You can go from India to Africa via this route. Okay, so you can go via this route, which means the diameter should be 2, because the maximum distance is 2. Otherwise the adjacents are very simple, one step process. So the maximum distance was 2 and the diameter becomes 2. What about this? Can I say here the diameter is infinity? Yes, we can say, because this player is disconnected. Okay, so India to Africa, no route, infinite time. What about this thing? Can I say again disconnected? No, they are connected. See carefully. If you want to go from this point to this point, you will go 1, 2, 3. 3-step process. D3, diameter is 3, because that is the only maximum distance you will get. Okay. As you have seen in the examples, we have to manually analyze and get the answer. So there is no direct formula in the bipartite, but in the complete bipartite we have analysis and formula. See, complete bipartite means k, m, n. So when m and n both are 1, in that case the diameter is 1, but apart from those the diameter would be 2. You can take examples and you can verify that. If I take k, 1, 1, so one vertex here, one vertex here, every vertex is connected to every other vertex from the p set to q set, right? So if you see, the diameter is what? Diameter is 1 here, because distance is 1. That is the only distance. So that is the only diameter. If I take k, 1, 2, one vertex here, two vertex here, connected, you can see distance becomes 2 maximum. So diameter is 2. You take any other example, manually you verify. You will only get 2 scenarios. One scenario when m, n both are 1, then the diameter is 1. Apart from that, any example you take, diameter will always be 2. You can take complex examples as well. You will always get the diameter 2. Do you want me to take one example? Okay, I will take one example, 2, 3. So 2 vertex here, 3 vertex here. Every vertex is connected to every other vertex. This is the graph. You choose. You want to go from this vertex to this vertex, 1 to 4. Try. So 1 to A, then A to 4. Diameter 2, distance 2. Okay, you want to go to this vertex. Okay, so 1 to P. If you want to go, then 1 to A, then A to P. Distance 2. So you take any example, you will get distance 2 maximum, and that is your diameter value. Easy. So this was all about the diameter of the graph. What is the diameter? How to find it? And through distance, we find the diameter. And how to find distance? The minimum number of edges. And to find the minimum number of edges, we have tricks, right? So use the tricks, opposite vertex trick, to solve it fast. Otherwise, it would be very time taking. Now going to the next concept, which is operations of graph. What are operations of graph? Since graph is dealing with set, and set operations will come here, union, intersection, complement, so on and so forth. So all those operations you have to see now in the lenses with respect to the graph. Concepts you know already. What is a union? Gathering of every player. So vertex of G1 union G2, take vertices from G1, take vertices from G2 and do the union, which means do the gathering. Okay, take all of them, all the vertices. Obviously you should not overlap the vertices, like if graph 1 is having ABC, graph 2 is having BCD, then you say that the union would be ABC. There also BC is there, but I won't repeat BC because already included BC. The uniqueness was D, so D come here. So gathering of all the players is done, ABCD, like this. Edges also, gathering G1 union G2 will be edges of G1 union with edges of G2. Try with this example. This is my graph G1. This is my graph G2. Do G1 union G2. So first you will always do the vertex calculation. Second you will do the edge calculation. So vertex calculation, copy this because it's gathering A, B, C, D. Do we have any unique player? A, B is already included. E is unique. So E here. Okay. So vertex done. First step done. Edges gathering. So again gathering is there. So whatever edges is here, draw it first. A to B, B to C, C to D, D to A. Okay. And now check here. A to B already included. B to E and A to E is there. B to E and A to E is there. And that is your resultant G1 union G2. This is how the operation is performed. First, write all the vertices. Second, draw all the edges. How to do it? Just gather them. Nothing tough here. But in intersection, you have to be cautious. But because in intersection, what you will do is, in intersection, first step is the vertices, second step is the edges. So whatever is common between us in vertices, that I will consider, and then whichever edge is common between us, that only I will include. If one edge is here but other edge is not there with A, I won't include. Same edges, A to B, okay, in intersection that would be included. If understood the very basic fundamental, then tell me if G1, G2 graphs are there, what is G1 intersection G2? Think. First step is the common vertices. A common, write it down, A. B common, write it down, B. E, C, D not common, so do not write. Now common edge, A to B is there, yes, A to B. That's it. That is our answer. This is our G1 intersection G2. As simple as that. No brainer. Easy. Now this one is tough. Complement of, not complement, it's complement. Complement of G. Okay. So what is complement of G? You know, in set theory we have studied, if A is the set, the complement of A was written as AC. And what is AC? Sample space minus A set. But here, instead of sample space in the graph theory, what is the sample space here? We have the complete graph Kn is considered as the sample space. That's it. This is what the basic fundamental concept remains. And now you can study. Okay. GC is the symbol for the complement of the G graph. So vertices will be same only. There is no difference in G and G complement graph. Both will have the same vertices. Very first thing to note. Second thing to note is interesting and important. Edges in the G complement is edges from the Kn minus edges from the graph G. With example it would be crystal clear, but for now you got the basic analogy and idea. Using the set theory concept of complement to connect in the graph, first thing we did that, and instead of sample space, what we are considering the Kn graph. You can see the essence here as well. But what interesting we noted was, interesting point was the vertices in G and G complement are same, but the edges are different. Edges present in G should not be there in the G complement. Then which edges should be there in the G complement? Edges in the G complement would be edges from complete graph minus edges from the G graph. As simple as that. Now let us understand this by example. First example I will solve, later you can solve. So if I check the first graph, this is G graph, this is G graph. We have to find G complement. So G complement is Kn minus G calculation we have to do. So Kn, how to find Kn of this graph? Every vertex is connected to every other vertex. So A, B, C, D, every vertex connected to every other vertex. This is what the graph looks like. Understood? Now Kn you have drawn, Kn minus this thing will give you the GC edges. But if I talk about the vertices in GC, as same as the G graph, vertices straight away you have to copy, but edges would be Kn minus GC edges, not GC, Kn minus G edges. Okay, so I can see same I have to erase. So DC gone. Okay, CB gone, AB gone in subtraction, DA gone. So basically the uncommons will remain. So Kn has this cross as uncommon with G graph, and that will remain, and that is the answer. As simple as that. You have to check in this graph what is not common with G, and that not common will be plotted in the GC. Simple, easy. If easy, then this is what your graph looks like. This is your GC graph. Find the rest. Tried? Pause the video, try. Easy. I guess there is no toughness here. There is actually no toughness. Very easy graph. So this thing is same, like if I want to write the Kn would be same as the above. Just do the copy paste. But GC would be different, because GC is, vertices are same. Vertices are A, B, C, D. Vertices same. Edges are like, in this two graph, the common part you have to erase. The uncommon part is written here. The uncommon part is this line CB, and then the crosses. That's it. These are the uncommon. Other players are common, so I will remove. This is our GC graph. Easy to find complement of the graph, not that tough. What about this thing star? Okay, if I want to make Kn, every vertex is connected to every other vertex. So I will say CB, CD connected, BA, AE connected, DA. So now I can say every vertex is connected to every other vertex. Check it out. C is connected to A, B, E, D. Similarly, A is connected to C, B, D, E. Every vertex is connected to every other vertex. Check it out. If that is the case, now talk about your G complement graph. You will say, sir, the vertices remains the same. Makes sense. Makes sense. But sir, the common players you have to erase, so that star structure I will erase, and that uncommon will be written here. So the uncommon was this pentagon, so that pentagon will be remained here, and that is your GC graph. Easy. So it's a two-step process. First step, copy the vertices, and second step, edges. The uncommon edges you have to write. Uncommon between whom? Kn and G. The uncommon edges you have to plot. As simple as that. Now here we have some observation. The observation is, all these graphs are connected. You can check if you want to go from C to B. It's not like it's disconnected and the distance is infinity. No, it's connected. C to D, D to A to B. Okay, connected. Here also everything connected. Here also everything connected. Like if you want to go from D to C, you can go from D to B, B to E, E to C. Right? You can go like this. So every vertex is connected to every other vertex. But if G is behaving like this connected, G complement is not like G complement is also connected. G complement is getting variation. It can be connected or it cannot be connected. It can be disconnected. So for every connected graph, the result is G complement can be connected or disconnected. Check. If I want to go from C to B, you will say, sir, C to this point to this point, but apparently we do not have any vertex at the center. See, we only have 4 vertex. So from C to B, there is no joining. So it's a disconnected graph. I hope this part is pretty much clear. Suppose we had one edge here, then it's no more disconnected, because then C to A to D, D to B. But for now it's disconnected. So you can see G was connected, but G complement is disconnected. But here G is connected and G complement is also connected. Here G connected, G complement is also connected. Like if I want to go from D to A, it looks like disconnected, but it is not. C, D to B, B to C, C to A. It's a connected graph. I hope the first note is pretty much clear, that if G is connected, then G complement may be connected, may not be connected. But if G is disconnected, then surely 100% G complement is connected. Any example you can take. The null graph phi 2. So our graph G is what? Disconnected. If you draw the complement, what would be the complement? Kn minus G. So Kn minus G, when G is null, then answer is Kn graph. Can you see connected graph? So that is the thing. Whenever G is disconnected, then GC is always connected. 100%. Now the third keynote is G union G complement is Kn, and you know very well why so, because G complement was Kn minus G. So if you rearrange, G complement plus G is Kn, so you can see that union of G and G complement will always give you Kn, and intersection will give you what? Intersection will give you null, because the definition was itself that whatever is uncommon between this and this, you have to write here. So uncommon, you can see the graphs G and G complement, the edges are what? The edges are uncommon. So if edges are uncommon, G intersection G complement would be null. In vertices format, they will have all the vertex same. Okay, in vertices, G complement will have the vertex same, G intersection G complement will have the vertex same. This is all about the edges. This story is for the edges. What happens in the edges? Not in the vertices, in the edges. Easy? Okay. Let us see some example. Example 1 in front of a screen. Pause the video, try, then look at my solution. Tried? So order of G graph is given as phi. What is order? Order is number of vertex. N is given as phi. Edge is given as 7. Can you find the order of G bar, which means G complement, and edges in the G complement? Yes, we can. How? Because we have studied G complement is basically Kn minus G. By the simple concept, we can solve a lot of questions. See carefully. Here they are saying number of vertices is phi. So same number of vertices will be there in the G complement. So G complement order means nothing but the number of vertices. Number of vertices in G complement and number of vertices in the G are same, and that is nothing but phi. So we got the answer. But edges are not same. I told you, in edges everything is different. Edges, everything is different. So for the edges, what we should say? For the edges, we should say edge in the G complement is edge in the Kn graph minus edge in the G. So edge in the Kn graph, when n is phi, then edges for the K phi minus edges in the G graph is given as 7. Edges in the K phi would be n into n minus 1 by 2, like this. So if you do the calculation, this is 4 by 2, 2, 5 to 2, 10, 10 minus 3 is 10 minus 7 is 3. So edges in the G complement would be 3. Number of edges is 3 and number of vertices are 5. Easy. To the next question. Pause the video, try, then look at my solution. The size of G and G complement is 10 and 11 respectively. Find the order of G. What is order of G? Order of the G is nothing but number of vertices, and it's same for both G and G complement. Okay, we know the relation. G complement is Kn minus G. And whenever they are talking about the size means number of edges. So they are talking about number of edges in the G complement. This is not G complement. First one is for the G and second one is for the G complement. This is the player. Okay, so number of edges in G complement is the number of edges in the Kn minus number of edges in the G. So number of edges in G complement given as how much? 10. Number of edges in Kn is n into n minus 1 by 2, and that's what ultimately we need, n value. And number of edges in the G graph, it is given as 10. Okay, so rearrange, not 10, I'm doing something mistake. Edges in the G complement is 11. Please make a note. Edges in the G complement is 11. Okay, so now minus 10 goes there. 11 plus 10 is 21. 21 is equal to n into n minus 1 by 2. Now there is two way. Either you make quadratic and solve, or you use simple maths to get the answer. Substitute and check. N is 7, then 7 into 6 by 2, 2 1s are 2 3s are, makes sense. So n is 7. Understood how to get the answer. How did I did n is 7? 21 is splitted 7 into 3. I was checking, is it matching here? So apparently it was matching. Okay, that's it. Okay, we have one more example, final question of the day. Pause the video, try, then look at my solution. Based on the same simple concept, the concept of complement of G. I hope you have tried. What was G bar or G complement? That is nothing but Kn minus G. Now Kn is not given but G is given. Kn is not given but G is given. So minus G. G I will write. You may write in any way. Either you write in your descending format or ascending format. Given is ascending. I am writing in the descending format. Anyway you can write. I have no issue. And what is Kn here? Kn is a complete graph. Every vertex is connected to every other vertex. How many vertex will be there in the graph? Check. 1, 2, 3, 4, 5, 6, 7. 7 vertices are there. So from the given data we have understood n is 7. So if 7 vertices are there, then maximum degree is how much? 7 minus 1, which is 6. So Kn says every vertex is connected to every other vertex. So if that is the case, every vertex will have the degree 6 because maximum is 6. So everyone will have 6 since every vertex is connected to every other vertex. 3, 3, 6, 7. Okay. Now do the calculation. 6 minus 5, 1. 6 minus 4, 2. 6 minus 3, 3. 6 minus 2, 4. Then 6 minus 2, 4. 6 minus 1, 1. 6 minus 1, 5. 6 minus 1, 5. Let me recheck. 1, 2, 3, 4, 4, 5, 5. Okay, so I got the answer. 1, 2, 3, 4, 4, 5, 5. That is our answer. 1, 2, 3, 4, 4, 5, 5. Okay, so either you writing ascending or descending form, whichever way you write, but that is our degree sequence. Understood? That is the final answer. I hope you enjoyed the class. It was a bit lengthy but not that tough, right? Diameter, distance, and some operations we have seen: union, intersection, and complement. Complement was easy because we have understood complement connected with the set theory where A complement was sample space minus A. Here instead of sample space we have the complete graph. That's all. On that basic we have understood how to plot graph, how to solve various types of questions. Thanks for watching the lecture.